Good morning, good afternoon, good evening to you all. Welcome to the 8th day of the online advanced course on Biomedical Imaging 2024. Today, we will have a panel of experts to talk about CT. I would like to remind you that you can send your questions via the Q&A chat box or express your intention to ask the questions orally by activating the raise the hand button. All questions will be answered at the end of each talk. Now, without further ado, I give the floor to Professor Ana Salomé Pires from the Faculty of Medicine of the University of Coimbra.
Thank you, Eurico. Good afternoon to you all. Today, as already said, we have the pleasure to present you an excellent panel of experts to talk about computed tomography, and also a new topic included in this year's edition of the course Biomedical Imaging, namely addressing the topic dosimetry and radioprotection. And to start, I am pleased to present you Professor Augusto Silva. He is Associate Professor at the Department of Electronics, Telecommunications and Informatics of the University of Aveiro, and he is also researcher at the Institute of Electronics, Engineering and Informatics of Aveiro. With an extensive curriculum in image processing, medical imaging, and imaging informatics, today he will give us a lecture on the physical basis of computed tomography. Thank you so much, Professor Augusto, for being with us again. I give you the floor to you, and you can start presenting your slides. Thank you. You are muted.
Okay.
Okay.
I think you can hear me now.
Yes, perfect.
Is that okay? Okay.
Yes.
So thank you again for the invitation. It's always a pleasure to join you at this event and talk about X-ray computed tomography. Mostly, I would dare to say some of the mathematics and physical aspects behind those fascinating images. Okay, so this is the outline. We always start by looking at some pictures because it is.
I'm sorry to interrupt
Yes?
you. We cannot see your slides yet.
Again? Oh. Share screen. I'm sorry.
No problem.
I'm sorry. Screen. Oops, what happened with the slides? What happened with the slides? This is screen one. Share screen. Because my screen two is not appearing. Are you seeing any slides now?
Not yet.
Not yet.
Oh, yeah, now we can see it.
Is it okay? I'm sorry. So we will start looking at some pictures because it's always insightful to start thinking about some peculiar aspects of computed tomography images. Now we will address in a simple manner, I hope, some of the mathematical highlights behind standard X-ray tomography. Then we'll evolve briefly to volumetric imaging, and we address as the last part of the presentation some issues related with new algorithms based on iterative methods, and also briefly some of the current trends regarding machine learning reconstruction. So when we look at these images, we see excellent contrast resolution, excellent spatial contrast spatial resolution. Okay, this is a unique trade-off that distinguishes computer tomography from any other X-ray based modality. Okay, so from many years now we have excellent spatial resolution and excellent contrast resolution. I'd like to say briefly that please don't confuse spatial resolution with matrix images. Okay, of course, matrix images are related with spatial resolution, but it is not the same thing. It is not the same thing. Okay. So Professor Caseiro Alves later on will talk about this peculiar mapping between the intensity values and the tissues. That's one of the main reasons that we have excellent discrimination, organ discrimination, lesion discrimination. Okay, so in fact, what we are seeing, what we are mapping, is what you are obtaining is a spatial map of linear attenuation coefficients, normalized with a particular scale that basically divides the attenuation coefficients by the attenuation coefficient of the water. These units are called Ansian units, in a certain way to pay tribute to Geoffrey Ansfield, the father of the modern CT, Nobel Prize of Medicine. Okay, so nowadays we have, as I said, excellent contrast resolution, spatial resolution, volumetric covering. Okay, the notion of isotropy is nowadays possible. We have our voxel elements, at least if we don't clarify the clinical protocol, they may be made equal. So we can, in fact, have excellent 3D post-processing procedures. So that's another aspect of nowadays computed tomography machines and systems, including software. Okay. So without isotropy, these types of images are difficult to obtain. Okay. So no interpolation required here. Excellent overview images. Okay. And the current workflow of an acquisition starts obviously with patient preparation, the choice of the clinical protocol to perform the acquisition, and then there is a loop that can be resulting from iterating between reconstruction and visualization. Nowadays we have retrospective reconstruction, and we can loop between reconstruction and visualization procedures, including post-processing, doing the fancy 3D post-processing. Okay, of course, we should always have a report, and somewhere images are archived as well as the reports. Okay. So this is, I'm sorry for the marketing. This is a Siemens Sensations 64 CT scanner, which is a well-known CT scanner. Okay, this is a modern view of a CT scanner. On the other side, the right side, we have the inner view of a gantry. It is an old picture, but it always impresses me because of the instrumentation that is embedded in this structure, which may weigh over a ton and is supposed nowadays to rotate at fascinating speeds, 0.25 seconds per rotation, which is something that induces a tremendous mechanical stress on the components, mostly on the X-ray tube. Okay, so back to the Greeks, we know that tomos means slice, and a long way has evolved from the original CTs from Hounsfield in early 70s to a current plane at CT. So what were the breakthroughs that were behind this path is something that is related with the physics, it is related with the mathematics, okay? So one of the things that I would like to stress is that for any medical imaging modality, look, we always steer some form of energy towards targets and tissues, okay? And then direct or indirect measurements or interaction of energy and tissues are developing, are measured in probably n-dimensional coordinate systems, and you can assemble all that all that information into a mathematical function. Okay, that depends on the coordinates. It depends on the time. For example, look at cardiac imaging, for example, where you need to consider time, and obviously the energy spectrum. Okay, so the idea is broadly, how do we synthesize, reconstruct, compute F from these measurements? Okay. In CT, I'm going to mostly speak about current fan beam geometries. Okay. We have radiation that transverses the body. So this is a transmission modality. Okay. And this is rotating and measurement geometry, rotating only. Okay, you have an arc of detectors. We will later on discuss how many detectors. Okay, and how many positions should be considered for the X-ray tube. So we gather a huge data set of, I'm going to say the name, raw data, projections. Okay, so that's what we collect. So in fact, we collect attenuation profiles, okay, which are then normalized. But what the row of detectors measure is are attenuation profiles distributed over sufficiently large number of X-ray tube positions. Okay, so the mathematics here is extremely facilitated, because X-ray wavelengths are small enough. So we may consider that the path of propagation is a straight line. Okay. So in fact, if you consider a beam or a ray, we have intensity in, intensity out. Okay. So the detectors, the solid state detectors, produce a signal that is proportional to the logarithm of the detected over the incident radiation. And we know that we can approximate this measurement by a summation. Okay, by a summation that is mostly proportional to the linear attenuation coefficient multiplied by the length of the voxel. Okay, so the idea is you have straight lines. Good for us, otherwise the mathematics will be much more complicated. So we collect projections and we have to go back to reconstruct the inner structure of our body. Okay, so this is called an inverse problem. If you do some Googling or ChatGPT or whatever, if you talk about inverse problems, mostly you end up seeing reference to tomography or X-ray tomography. Okay, so I leave you with some important names: Radom, Katzmarx, and Cormack, which were which made important contributions to the theory behind the reconstruction that paved the way to these excellent quality images. Okay, so this is a complex problem. Look, okay, if we have our body as a plane structure, okay, in fact, we can solve that analytically. But if you introduce a pseudo organ here, tiny pseudo organ, you complicate the problem. If you think of real slices with tissues, different structures, the problem is itself much more complicated. Okay, so how do we go back? The first approach that was behind the scanner of Hounsfield was built on systems of linear equations. Okay, we have measurements S, we have our variables, the linear attenuation coefficients, and we have an operator that describes mathematically this mapping between linear attenuation coefficients and the measurements. Okay, so theoretically we need to solve a system of linear equations. The bad news is that we have a huge system of equation that is very difficult to solve by traditional methods. Okay, and anyway, I decided to leave this slide here because recently these methods have gained more interest, I'd say more development because of the current trends of iterative reconstructions. Okay, so linear systems modeling is still a modeling concept for current iterative reconstruction. Okay, okay. Back in 1917, long time ago, this Austrian mathematician proved that if you know all these profiles, it is analytically possible to build the inner structure of a region. So this has nothing at all to do with tomography, but back in the mid 70s of last century, this mathematical model was introduced, and then we achieved a quite faster reconstruction method, which is still used every day, which is called the filter back projection. Okay. Let me make a little bit of a digression just to enlighten you about the sinogram concept. Okay. If you have, for example, imagine a tiny lead spot, very, very high attenuating material, and if you make a scan, our raw data is distributed because it's just a point over a sinusoidal profile. Okay, that's why we say that measuring projections in X-ray CT is collecting the sinogram. Okay, and what you have done here for a point may be performed with a collection of points. So many points as pixels in the image. So in fact, what we have as raw data is a structure like this one. Okay, which is, at least visibly, which has nothing to do with an image. So the fascinating thing here is that with an analytical reconstruction process, we can obtain this image. Okay, so the mathematical problem is given the sinogram computed image. Okay, intuition tells us that, okay, we have projections in our detectors. What if we do back projection? Okay, if we do back projection, it would have been a nice idea, but unfortunately, you have this kind of resulting images, useless. Okay, we have strict artifacts, we have blurring, and so on and so on. Okay, but anyway, this serves to illustrate the simple idea of back projection. So what the filtered back projection does is to get rid, by mathematical methods, of these tricks and this blurring. Okay, so whoops, a little bit of mathematics, but let me try to illustrate you. So this term here is our raw data. Okay, which is then back projected and then filtered. Okay, so we have here, in fact, three mathematical operators: projection, back projection, and filtering. Okay, don't bother with the details, but it's what we call in mathematics as a commutative operation. So we can obtain our projection, we filter the projection, and we back project again. So this is why we call this filter back projection. This is still the main workhorse, I would dare to say, of analytical reconstruction methods. Okay. One of the interesting things that we can notice about this formula is that this term here. This term is to conclude the filtering. Okay, and the reason, because I would like to speak about this, is because it has a tremendous impact in image quality. Okay, so this is what we call the frequency response of the filter, or the impulse response. Look, maybe we look at the impulse response, the response to a point, that tiny lab point. Okay, look, it means that when we reconstruct, we don't have an infinitely thin pixel. We have a response that covers more than one pixel. I'm speaking about spatial resolution. Okay, so an infinitely thin point is not reconstructed as an infinitely thin point. It has a little bit of blurring, and the choice of the filtering conditions the blurring. Okay. Of course, CT technicians are not used to speak about convolution kernels or filters or whatever. They are used to terms like the lung filter, or the head filter, or the abdominal filter, and so on and so on. Okay, because these are built-in filters provided by the manufacturers, Siemens, GE, Toshiba, etc. Okay, so this is a very important choice for the image quality. Okay, let me show you an example. Here you have a very tight, very sharp impulse response. You have good spatial resolution, but you also have noise. Okay, here you have less noise, less visible noise, but details are more blurred. Okay, so the clinical protocol is the one who dictates the choice of these filters. Okay, so staff should be aware of what they are doing regarding these choices. Okay, so what happens, in fact, is that we sample our body section with a huge collection of X-rays, X-ray beams. Okay, so you may ask, how many detectors should be here? How many X-ray tubes should be here? And the answer is it depends on the scanner geometry and on the high contrast spatial resolution that is desired. High contrast spatial resolution is measured normally in cycles per millimeter. Okay, so for example, scanners like Siemens Somaton 64 propose the scanner resolution at 50% decreased response as 2.7 cycles per millimeter. Okay, there are some formulas, but I think it's enough to say that please expect to have here about 700 detector elements, and expect to have between 900 at least 1,000 X-ray positions. Otherwise, you start seeing artifacts, okay, in the image. So the FBP, the filter back projection, was in fact breakthrough in software in mathematical basis of reconstruction. Okay, and today it is benefiting of special purpose hardware. Everybody is aware of GPUs and have heard about NVIDIA GPUs and so on and so on and so on. At the end of the day, this type of computing engines was like a glove to improve the efficiency and the speed of a reconstruction of these kinds of algorithms. So each manufacturer has its own purpose, the special purpose reconstruction hardware. Okay. Anyway, this technique is, I would say, high dose friendly. Okay. If you want to perform for example, screening procedures where you want to minimize the dose, chances are that the filter back projection algorithm will provide not so good images. Okay, so the FPP has its own limitations. For example, metallic processes are terrible things for the FPP. Okay, and the FPP requires standard geometries and complete data. Okay, so you should complete at least 180 degrees to have minimal data set to perform reconstruction, which means that you don't have a speed improvement as much as we'd like. Okay, I have to talk about this. Okay, because nowadays CT is a volumetric modality. Okay, but what has made this volumetric imaging standard procedure was a couple of breakthroughs. The first one is the single slice spiral, the spiral technique, which means you move the patient table at the same time you move the X-ray tube. Okay, and the other breakthrough was the multi-slice spiral technique. So instead of a row of detectors, you can have 4 rows, 16 rows, 256 rows, and so on. Okay, so slip rings date back from the end of the 80s, last century. Multi-row solid state detectors start appearing before the 2000. Okay, here, and from then on, we have assisted to gains in speed. We have seen architectures with multi-source gantries. So instead of a single tube, you have, for example, two tubes. Okay. We have C-arm tomography, which deviates from the traditional geometries, and recently we have commercially available, very expensive, photon quantum solid state detectors. Okay. So these slip rings made a breakthrough because they allowed to provide power to the X-ray tube in a continuous manner. It provides a way to collect X-ray measurements in a continuous manner. Okay, so I state the slip rings as no doubt about that major breakthrough in the CT evolution. Okay, so this is what I say: simultaneous movement of patient table and the X-ray source. Okay, but next slide it will be just to highlight one of the immediate advantages of the spiral CT. Okay, so look at this. This is sequential, traditional. Okay, if you have a lesion here, okay, the best case is an image with this profile. The worst case is an image with this profile. If we have two tiny lesions, the best case will be possible identification of these two lesions, and the worst case is a blur, complete blur. Okay, that does not happen with spiral CT. Okay, we can perform acquisition protocols that perfectly allows the reconstruction of these tiny lesions that are very with a very small distance apart. Okay, I'm going to skip this this slide, just to say that Spiral City allowed one of the things that enables the reconstruction loop, which is retrospective reconstruction. You collect the data, all the slices, you cover the patient, and then you perform reconstruction. Okay, one time, two times, and it's the times that you decide. Okay, since you have your raw data inside the memory of the system computer. Okay. Okay, spiral means requires interpolation because we have, in fact, to obtain in-plane slice. Okay, so I'm just going to bypass this slide, so show you the images that happen if you don't do interpolation. So we build a useless image. Okay, and this is a useful image with interpolation. Interpolation is in the basis of many advanced algorithms that are available in the multi-slice current scanners. Okay, another parameter that is interesting is the pitch, the ratio between the helical step and the or table field per rotation and the collimator aperture. Okay, if you do want speed, you have to have large pitches. If you want to do, for example, coronary imaging, you have to choose very small pitches. Okay, so this is dictated again by the clinical protocol. This is an approach of the slide, an approach to understand the effective slice thickness. Okay, when we speak about, okay, I have 1 millimeter slice thickness with a spiral machine, we are talking about this. Okay, so somewhere is the pitch inside this formula. Okay, again, pitch is governed by the clinical protocol. So, for example, this is the timeline of the multi-slice world. Okay, in 2017, we arrived at 384 slices. I guess is a Siemens CT scanner, or especially for cardiac imaging. Okay, so the mathematics is a little bit different, but lots of interpolation. Filter back projection still prevails. Okay, so this is what we can do with the isotropic imaging. Okay, multiplanar reformatations with excellent quality. You can view transaxial slices. You can view coronal slices, sagittal slices with great qualities. Okay. So nowadays, the detectors, the matrix detectors, are solid state. Okay. The majority of them are hybrid solid state detectors. They have an optical layer in between. Recently, machines with photon counting imaging have emerged. Okay, with great improvements in spatial resolution, paving the way for multispectral imaging, and so on and so on. Okay, I'm going to skip this. So lots of interpolation because we have many slices. Okay, to contribute for many row acquisitions that contribute for a slice. Okay, each vendor has its own reconstruction algorithm, which is tightly protected. Okay, vendor locked. I give you some of the names. And nowadays, we started to view or assist that manufacturers provide iterative reconstruction methods. So iterative reconstruction methods are not new, okay? Are not new. They are, as I told you before, based on linear equations system modeling plus noise. It is more or less generally accepted that better image quality can be achieved, mostly with lower acquisition dose. Artifacts, metal artifacts, for example, are minimized. So there are some important advantages that iterative reconstruction provides. And since dose reduction is almost a mandatory requirement, every manufacturer is offering his own iterative reconstruction method. Okay, so the idea is relatively simply, I guess. So we have a loop. We have a loop. Okay. We start with the first image estimate, which may be a very nasty filter back projection reconstruction. And then mathematically, we forward project using GPUs, for example. Okay. Okay. We compare with the measure projections. And upon the error, we correct the images. So we live in this loop up to the point that the algorithm says, okay, that's enough. We cannot converge anymore. Okay, so this is the general framework for iterative reconstruction. It takes obviously more time than the filter back projection. With no surprise, vendors do lock their algorithms. Okay, so we have Iris and Sapphire for Siemens, HiDose for Philips, Asir and Veo for GE, and so on. Okay, so it's impossible to provide you the details much of these algorithms since they are vendor locked. So here we have a couple of images that illustrate the usefulness of the iterative reconstruction. Okay, so mostly noise reduction with low dose acquisitions, for example. Okay, artifact reduction. This is still an ugly image, but better than this one. Okay. So this is an imaging CT angiographic study from the carotid arteries with a patient with a metallic dental hardware, as they say. Okay, so artifact minimization. If this is useful, I don't know. I leave you to the clinic. I leave this to the clinicians. Okay. Angiography imaging at lower doses. Okay, I hope that you can see or perceive the grainy noise over here and a much more smooth image in this middle image. And of course, this is a I guess a 3D reconstruction of the whole set. With no surprise, machine learning is also reaching computed tomography reconstruction. Okay, it is not to substitute. It is not. They are not a replacement to iterative reconstruction methods, but they are proving some advantages, mostly in denoising. In denoising denoise the reconstruction. Okay, The bad news is that, as any deep learning framework, we require large training data sets. Okay, long training periods. Okay, and dedicated hardware to achieve this. I'm speaking about again GPUs and so on. Okay. So let me. Of course, we are speaking about neural networks. Okay. With which is a biologically inspired computational engine. Okay. And the interesting thing is that each unit here performs multiplication and a summation. Okay, which is very fastly computed using GPUs, for example. Okay, so we have to train these networks, and training means guessing these numbers, these so-called weights. Okay, millions of them, millions of them. Okay, 50 million, 60 million, and are typical numbers. Okay, and this is very data dependent. Okay, so if you do machine learning reconstruction for thoracic CT, it won't perform as well as we expect using these techniques to reconstruct head CTs, for example. Okay, so this is a general overview of the traditional CNN architecture for denoising. Okay, we provide in training with the model, the deep learning model, with the pairs of images. Okay, low dose, high dose. Okay, meaning that we are saying we are supervising the system to say that okay, given a low dose images, we are expected to produce high quality images similar to the high dose filter back projection image. Okay, so that means that in fact we are data dependent, anatomy dependent, and we do need lots of training images, for the sake of generalization. Okay, as far as I know, there are two vendors that provide FDA approved deep learning algorithms. One is for GE, the other is for Canon, I guess. Canon or Agfa, I think it's Canon. Okay, so this is the training path. Okay, takes a lot of time, a lot of computational resources, but the inference is surprisingly fast. You can reconstruct hundreds of slices in a matter of seconds. Okay, it's very interesting, this facility of the speed of the inference of deep learning methods. Okay, so this is typically for denoisings, and there are some initiatives that go directly from sinogram, okay, to images. So the paradigm is sinogram in, image out. Okay, there are publications about this. I guess it is not FDA approved yet. Okay, it is supposed to offer us good quality reconstruction with low dose sinograms also, okay? But it's a different paradigm. Training is based on sinogram in, image out. Everybody is acquainted nowadays with generative AI. So one of the ways to achieve this sinogram in, image out is with generative models, or GANs, or generative adversarial networks. Just keep the name, okay? Keep the name, because it's something that you can find in the literature. And yes, it is true that generative AI is arriving at medical imaging. In this case, particularly, it's arriving at CT reconstruction. Okay, so these are some figures of merit. Okay, I'm going to end rapidly. Okay, you see here the quality at low dose. Okay. Excuse me. Okay, you see here the depiction of low contrast objects. Okay, so this is a technical evaluation. This is a clinical evaluation. Okay, this is FPP, which is useless. This is deep learning reconstruction, which is quite useful. Okay, so key drivings, modern CT, volumetric acquisition, undissolved slices, submillimetric voxels, isotropy, great deal of image post-processing apps. Okay, for these studies, if you include the time, or if you include multispectral, a trend to substantially reduce the dose, a trend to improve our speed. Okay, and as I told you, machine learning is arriving at the world of CT reconstruction. Okay, so this is our a bunch of specs that I leave you with, just to put numbers on this. Okay, put numbers on this, and there are lots of topics that are worth to probe further. Okay, I'm not addressing here anything else than performance metrics. I guess Professor Caseiro will talk about something later on about dual source or spectral CT and so on and so on. Okay, so lots of topics to probe further in other courses. So I thank you very much for the opportunity, and I hope to raise some interest on you about this fascinating modality. Thank you very much.
Thank you so much, Professor Augusto, for this very nice overview. We have time for a few questions, and I will start with the question we have in the chat. So, what is the impact of volume partial effect? Yes, you can see it. What is the? Yeah, I will read for everyone to be able to listen to the question. What is the impact of volume partial effect on the reconstruction, and how thinner slices help to reduce this type of effect?
Okay. When you talk about thinner slices, we are talking about improving the Z spatial resolution. Okay, thinner slices. And we try to get rid of, in fact, of the partial volume effect that we inevitably have with not so thin slices. Okay. Anyway, as I guess as I remember, I told you, the clinical protocol is mandatory here. Okay, because there are the clinical protocol, there are those issues. Okay, so we cannot go for arbitrary thin resolutions. Okay, unless the clinical protocol dictates that. Okay, but partial volume has an impact on the quality of reconstruction when you do slices like 2, 3, 5 millimeters thick. Okay, that's for sure.
Okay, thank you. I have also one question and one curiosity regarding the photon counting detectors that you talked about. Are these detector or will these detectors be able to improve the compromise between the radiation dose and image quality maintenance?
Definitely, you can expect a gain of moving from 0.7 millimeters to 0.1, 0.2. Okay. Okay. With the same those specs. Okay. Okay. You can expect that. Okay.
And my curiosity regarding this is if these detectors are already part of the clinical CT scanners that are used nowadays, or if they are in the research.
I guess Siemens has a scanner that is already deployed in the clinical environment. Okay, I don't know the others. I know that I should have learned the name of the machine, but you can find that very quickly.
Yeah. Of course.
Okay. But there is they are in the clinical environment. I think they are pretty expensive.
Yes, that's why my question, because you refer they are pretty expensive.
Yes, they are quite expensive. Okay.
Okay. So we do not have any more questions. I would like to thank you again, Professor Augusto, for your collaboration with us again, and thank you so much.
Okay, thank you very much. It's always a pleasure to be in Coimbra, online, in person, or whatever. Okay.
Thank you so much. So
I'm sorry, but I have to leave now because I have an appointment. So my excuse to the Professor Caseiro, I always like to hear him. So I think the next opportunity will be in the same place. Thank you very much.
I just want to say one thing, if I may, before you leave, is that I was not able to see your talk, but this is due because I'm in the middle of a congress. So this is the reason why I was not able to attend your conference. Very sorry for that. I know that they are always very interesting, but I will try to do my best. I already know because I have accompanied what you have done last year. So I will
Professor,
go in this continuation. Thank you very much again.
Thank you. Thank you very much. See you next time.
So then we will move on with our program, exactly with Professor Filipe Caseiro Alves. Thank you again for accepting this second invitation to speak at our advanced course in biomedical imaging. As a familiar face from yesterday's session, I will give him the floor to begin today's talk on the topic of computed tomography, technical update for clinical applications. So Professor, whenever you want, you can start, and thank you so much for taking this time from your congress and be with us. It is always a very profitable time to listen to you. Thank you.
Thank you very much. You're very kind, and thank you for the introduction. I want to salute everybody, especially Professor Filomena Botelho, a good friend and colleague from the university, also the Austin Initiative. It's a pleasure to be here with you. And I'm very sorry if some of my slides are in Portuguese, but they are not very text filled in. So it will be easy, I think, to follow, but nevertheless, be free to ask at the very end or the chat or whatever, any doubts you may have. I don't know exactly what are the persons that are here, what is their background. If I suppose they are not radiologists, we are in the middle of a biophysical course, so I will try to show to you what, in the continuation of what Professor Augusto Silva was saying, trying to use some clinical applications. Now, so what we do with all these parameters and physical principles that were so well explained by him. And I will try to go to my first slide. I'm very sorry. Okay. So this is the summary. I will just go briefly because, sorry again, in Portuguese. So just the brief physical fundamentals of the multi-slice CT. I think this is important because it's made a huge change on the clinical scenario. The parameter of acquisition, the strategies for reduction of dose. This is a huge concern, especially when we know that this began, I would say, by a publication in the press in the United States showing that children that were submitted to iterative examinations of angiographic CT of the brain, and they were beginning to be with alopecia, and is one of the major possible side effects of radiation. And this created an enormous discussion on the media, then transposed to the clinical scenario, and then finally we are now using very bold strategies for dose reduction. I would like to discuss this with you, especially using the new techniques, as I've already heard here of photon counting CT. I will talk to you about what are these clinical applications that are so important for us, why do we need them, what they mean to us, the 3D and 2D reconstructions, what have we gained, and then at the very end, I will talk to you about the new developments. This means functional imaging, deep learning, and photon counting. So this is the summary I had prepared for you. And of course, I always like to see one of the Nobel Prizes was received by the physics. And again, for imaging, we received so many prizes since the discovery of X-rays that it's incredible. And this is a tribute to Sir Godfrey Hounsfield that received the Nobel Prize in '79. And this is the first model that was prepared for this topic. So with CT, you already, I think you know what we are talking about, how it works, and the rotation from the X-ray tube that you with a collimated radiation, and that is going to hit the detectors. And the majority of the modifications, again, all this principle of tomographic with 360 degrees around the patient has been the same. The difference is the way we explore it, the number of detectors, and finally the quality of the detectors that has changed in the present past. So today, basically what we do is to continuously produce radiation X, and this shows you the modification that we had just in 30 years. As you see, the first machines were able to derive a very pixel-wise 128 matrices to go to the year 2000 to this kind of spatial resolution with white matter and gray matter, and the possibility to see the things with a complete different resolution. So this is, in fact, what we are able to perform today, images of a high, big quality. And just to note, we have not increased since 2000 the size of the matrix. We are still using the same. It's 512 by 512. And this is important. What we essentially change is the thickness of the slice for our image reconstructions. Again, just to remind that the conventional radiology is not prone is only prone to demonstrate 5 types of basic opacities, 4 that occur naturally, and the metal opacity that does not occur, as we know, spontaneously, and the need for introduction of contrast agents in order to see some of the things. But in fact, with CT, the difference is that we are able to detect much more densities using the arbitrary Hounsfield unit scale that typically goes from -1000 to +1000. -1000 meaning total passage of photons, like in the lung, where there is practically no attenuation. Just to remind that the normal lung attenuation, of course, it's not -1000, it's around -850, because, of course, there is soft tissues around also that we should also consider. Then we have the importance of the density of fat that we are able also to detect and characterize, -100. Then it's very important to characterize the water-based lesions, or like the CSF, the cystic lesions, whatever, with 0 Hounsfield units. And then we go on the positive scale, going from liver, spleen, muscle, aorta, great and white matter, something around 25 to 75 Hounsfield units. And very importantly is when we have fresh blood, due to the content of hemoglobin and the iron present in the blood, we are able to, in fact, to see spontaneously blood within the structures. And this is, of course, as you may know, is the rationale to perform CT in patients that have a stroke, acute stroke. And the idea is to be able to distinguish between ischemic stroke or hemorrhagic stroke. And this, of course, has completely different approaches from the clinical point of view. So the windowing is very important. Of course, I'm not going to elaborate a little bit more on that, but to show you the importance of the correct windowing using soft tissues, lung or bone, and all of them for very specific purposes. Here we can see a metastasis in the left adrenal, as we see here, or lymph node here, that is essentially cystic, showing that there is necrosis. Here with a lung analysis, we see a cavitated lesion in the case of tuberculosis. And finally, in this case, we have a metastasis in the spine, which is clearly demonstrated by the bone window. So this is just the first point. The second point is the possibility to use special algorithms for reconstruction of the images. And I think this is your level of expertise, I think, showing that if we ask the equipment to reconstruct with an algorithm that is able to show the high spatial frequency structures, what we can see something like that. We do not understand very well what's going here in the right liver lung, in the lateral lung. But if we do this with combined with very thin slices, we clearly see that there are tubular structures inside which correspond to a very defined pathological concept, which are bronchiectasis. And the treatment of the patient will be, of course, completely different if the patient has just a pneumonia or if he has chronic bronchiectasis. So we move also from a single slice CT or incremental CT to the initially to the 4-row CT. As we see, we have 4 rows of detectors, and this was, I would say, the very beginning. And then we have joined not only a number of detectors that are, of course, finite because of the geometry of the cone, the geometry of the cone beam, which allows you to do an angle that does not cause distortion. And due to that, the number of detectors that we can join in the same gantry today goes up to 250 but to tell you the truth, this is rarely used in the clinical practice. The most used are 64-row scanners. Why this is? Because with this, you can explore in the same heartbeat 16 centimeters of anatomy. And this means that what has 16 centimeters of anatomy is the heart. So this is essentially made to perform heart examinations in a single beat, freezing the movements of the heart, and be able to demonstrate not only the walls of the heart, but essential to perform angio-CT imaging of the coronary artery. So this is the new thing. Let me just take out the sound here. This is just to show what happens if we open the gantry, and to show what happens inside the gantry. This is the rotation speed, the real rotation speed of a 64-row scanner, multi-slice CT. And this is very impressive. Fortunately, this is the patients do not see this, which is good. And what we obtain is images like this. As you can see, there are no discontinuities in the axial plane. So we are using isotropic fossils, as Professor Augusto Silva was telling about, and I think was one of the questions. It is very important. How do we obtain this element on our images? Essentially using slices that are no more than 1 millimeter thickness. And with that, with higher matrices, we are able to have isotropic voxels. So we have new clinical applications. Let me show to you some of them. The z-axis resolution, the temporal resolution from 2 slices per rotation, 4 slices per rotation, supposing we have exactly the same conditions, or is just a modification of the number of detectors we have in the machine, or in this case, 16 slices per rotation. And you see the amount of anatomy we can cover. And this is the reason why, for instance, some hospitals now go further using this kind of technology for patients in the emergency care. No more radiographers are taken. For instance, in Canada, the gold standard is to use CT on the emergency care unit. If we do not want to cover such an amount of anatomy, we can use it to do thinner slices and to obtain the so-called isotropic voxel. Again, for our first experiment with 2 slides per rotation, 2.5 collimation, we cover this anatomy. With 4 slides per rotation, doing with a collimation of 1.5, we cover more anatomy, and even more 0.5 collimation in the 16 slides. So it's very easy to come, and this is the reason why today we do not call it anymore computed tomography. We call it, in fact, volumetric CT. And this is the idea, because in fact we can reconstruct wherever the plane. And here are 2 examples of isotropic voxel with a slight thickness in the limit, and the threshold is 1 millimeter or less. And here you have the quality of the images in the coronal plane or in the sagittal plane. And this is of utmost importance for our decisions and clinical decisions, and display, the morphological display of the anatomy, allowing to perform images like this. This is an example of angio-CT of the pulmonary arteries, which is the gold standard to rule out pulmonary embolism. As you can see, these are the pulmonary arteries, and you can follow the pulmonary arteries just to the subpleural space, as we see here, in a perfectly normal case without emboli. You can exclude them very easily. And since we are so fast, we can do this in something like 5 to 7 seconds to the patient with this image quality, and with an injection on a peripheral vein of contrast. Of course, I think that today, what is the game changer on imaging of the heart is, in fact, the coronary CT. And this is the kind of images we can obtain. We can do a display inside the vessel, doing some image post-processing, and you can easily quantify the stenosis, mean the stenosis, see the stents, calculate the rate of obstruction of the stent, and this is a very, very useful information that is mostly used to pass the patient to more invasive procedures, especially as cath lab for coronary angiography. Another point that is very easy to perform today is that we can have a parametric map of the density of the liver. We can do it with the patient in inspiratory apnea or expiratory apnea, just to try to detect and define the areas of air trapping and calculate the amount, the percentage of the pixels that in fact have a density that is minus 850. This means that we have some kind of emphysema of the lungs. So we are able also to measure the amount of emphysema in the lungs and to go to quantitative and to be able to do it to see if it is more on the right or the left, or this low or that low. So this is also important. For the reduction of the dose on CT, which we know it's one or is the most proeminent dose delivering technique that we have in radiology. First, the online modulation of milliamperes. This is very easy to perform because it's an automatic procedure, and the machine just goes and reads what are the thickness of the volume. They are surpassing the photons, and in fact, if we have the abdomen and we have the vertebral column of the lumbar spine, so we are going to have to deliver a huger amount of radiation, especially on the pelvis, as you see, due to the iliac bones, contrary to the lung, where the lung, of course, needs lower doses of radiation. And this concept today is also associated with another one that is very important, which is the iterative reconstruction techniques. I'm not going to enter on details. I think that Professor Augusto Silva has explained to you the principles, because normally what we did is the filtered back projection as initial building block is exactly the same for the raw data we have initially, but then we can use some kind of iterative applications on mathematical calculation that does not need to have the complete raw data resolved. And this is some kind of knowledge that came from nuclear medicine, because it's the way nuclear medicine do their examinations. But in fact, we are able to perform it very wisely because the computers now allow to perform these mathematical calculations very fast and denoise the images. So, of course, there are some drawbacks. I'm not going to enter on that, but look at the final goal. This is a liver that has 3 hypodense lesions. In this case, a simple lesion, they are cysts. But look now, we are doing with a slide thickness of 3 millimeter, and we have a CDI of the 30 milligray. Now, using the same machine with iterative reconstruction to 40%, using a reconstruction, a slide thickness that is of the same magnitude, we obtain the same resolution for the small hypodense areas with a CTDI of only 11 milligray. So we have decreased by 60% the amount of dose radiation we are delivering to the patient. And of course, this, as I told you, does not come at nothing, but here we have also the iterative reconstruction in the pelvis, and you can see that the anatomic information is exactly the same, with the minus 30% of MAs used to perform the image. Of course, we need to understand where can we go, and we cannot go so far that it will be totally impossible just to have quantic noise in our images. So we must stop at some level, and in this image, which is obtained with the 0.61 millisieverts, we see that using this iterative reconstruction, we are able to disclose this liver metastasis that on the filtered back projection is only noise, so we don't see it. So this is, I would say, the advantages of the using of iterative reconstruction, which is now the standard of care for CT in all machines. Of course, this, as I was telling, has some problems because the noise, the images gets a little bit different, and in some cases the reading of the images is not so easy to perform. So we need to know that also. But in general, we can go up to 40% of using of iterative reconstruction, no more than that. So this means less than 50% of the raw data, and we are in the safe side. If you use more than that, we introduce a lot of noise in the image, we introduce a plastic aspect in the image, and the diagnostic information begins to be lost. Just to show you also an example of what we do not lose, and look at this example, is a patient with bowel loops that look quite abnormal on the regular CT image, and using the ASIR, the iterative reconstruction, we can see very well the thickening of the wall and everything else. So all the information is here. We don't need to do anything else. And we have, in fact, used not 17.8 milligray, which was used for this image, but only 5.5 milligray to obtain that image. So you can judge by yourselves. Look at the images, it's perfectly interpretable and has the same diagnostic quality. So this has been shown by several papers. I'm not inventing the wheel here. It's just to show you that, in fact, many papers in the past, when this was initially presented to the medical community, and you can see that there is an enormous gain on low-dose imaging without any problem. However, we must think that the low contrast level can be hampered by using this type of reconstruction. We should know that because, in fact, when we are dealing with structures like, for instance, the liver, which is normally a low noise organ, we may lose things. And this is very important to understand that it cannot happen. Look at this image with routine dose filter back projection. There is a metastasis here. If you 80%, the lesion is still visible, so it's good to reduce. As I said, 60% of the routine dose, again, the image is visible. But then if we are going to decrease even further, it begins to be more and more difficult. Now, let's go and after speaking about this radiation reduction techniques that we are using in the current status of CT, also two new modalities that explore the capability of volumetric CT. So this has been coined CT, or the 3D CT. Let me show you some of the examples that are very important for the day-to-day, for the daily basis. And as you can see, here you have the multiplanar reconstruction. We can use a 3 reformatted multiplanar reformation. This means that, for instance, if you are or if you have acquired images 1 millimeter thickness, you can use this kind of software in order to increase, to virtually increase the thickness of the slices and increase and reduce your quantic noise within the image. Another one that was used, very used in the very beginning of 3D imaging of CT is surface shaded display. This is also a very simple approach when there is some kind of a combination of nothing or everything. So this means that we can say to the software to reconstruct only the pixel that at least some, for instance, 200 Hounsfield units or 600 Hounsfield units. And with that, and attenuate all the others. And with that, we can obtain images that in fact show only the surface of the organs. Then it appeared MIP. MIP is a maximum intensity projection. And the rationale is a little bit like the first one. The difference is that it is bidirectional. It's not a 3D technique, it's a 2D technique. And what we see here is essentially that we highlight all the pixels that contain contrast and attenuate all the pixels that do not have contrast. And so this increases the capability to see better the vessels, which at the very end migrate to the, I would say, the most important form of reconstruction we have, called volume rendering, when a color scheme is applied to the pixel values and is able to represent all the densities with different colors. So this was, in fact, what we have used. And to show you to some examples of one thing that is very important, the study of bone, especially curvilinear bones, and this is not a fracture. This is very well demonstrated that it is a normal variant within this hip, and of course in a patient with pain, and this is very important to make differential diagnosis. Do some oblique reformats or even freehand reformats, like we see here of the sacrum and the coccyx. Look at this fantastic image with all the nerves that pass in the holes of the sacrum, which are clearly displayed, or the possibility to obtain these coronal images from a wrist. This is the radius, and this is the cubitus, and we see here the bones of the carpus, and look at the quality of images and the sharpness we have. Also, this has contrast in between, meaning that we are dealing with an arthrography. The same, for instance, in the spine. This is very important in this patient with several vertebral blocks. The vertebral bodies are fused to each other. This is due to arthrosis, and then we have some elements that compress, as you can see, the dura mater, and also compress the spinal cord. So this is the kind of information. Of course, we can obtain it from the axial view, but look at the immense information we gain from going to axial to sagittal with the same quality. So this is really very important. Another typical application is to go to virtual hepatectomy. This is what I show here. We can calculate the volume of individual segments of the liver and ask the software to take out the liver that will go out and understand which will the liver that will remain in the patient. This is the cases of living donors of liver for transplantation purposes, especially on pediatric patients. And we see that we have all of this. This is the amount of liver that is more than enough. We can calculate. We know that one person must have at least 30 to 40% of normal parenchyma in order not to develop hepatic insufficiency. We can do also advanced imaging of the vessels in the liver. Look at this image. And here we have the vessels that irrigate the liver. This is the hepatic artery going to the right, going to the left. We can, in fact, see all the elements and be able to take better our decisions. Look at what I'm doing here is to show to you this case that I think it's important. We see a tumor here. You see the complete thrombus at the right portal vein. But we can say to the surgeon, attention, pay attention, you have a few millimeters of portal vein left here that may allow you to perform right hepatectomy and treat this patient surgically, despite this having a very cumbersome situation, which is a tumor thrombosis of the right portal vein. New applications. This is another one. It is called the virtual colonoscopy or colonography, as you may wish. And again, this was created by the possibility of insufflating air or CO2 within the colon. And due to the enormous difference in contrast attenuation between the CO2 and the walls of the colon, we are able to perform these images that are very anatomic, and the surgeons love it because they can understand really what is going on with the size of the colon, where are the flexures, where is everything. But most of all, you can go inside and see what happens inside the colon, like the optical colonoscopy. Of course, there are advantages and disadvantages of the technique. I'm not going to enter on this here because I think you are not doctors, MDs, but to tell you that it is an important technique that is complementary to the optical colonoscopy. And of course, the recent sun that we have for reconstruction is kinematic rendering. The difference between volume rendering and kinematic rendering is that we have even a more realistic approach to all the anatomy of the patient, as we see here with this patient with a huge vascular malformation of the right arm that goes here. As we see, we can decrease from the surface going more profoundly, and we can even go to the bone or use other algorithms. And this is very important because you understand where you can make the clips and make the cuts for a better understanding of your surgery. The difference of kinematic rendering from volume rendering is not enormous. The difference is that instead of having some kind of external light giving you the idea of 3D by the demonstration of illumination and shadowing, they have not one source of light, but hundreds, thousands of sources of light. And this creates this realistic apparent appearance that is called kinematic rendering. So let's go out now of the acquisition parameters, reduction of those, 3D reconstructions, benefits, and new clinical applications. Let's go to the artificial contrasts on MR. And of course, when we inject, basically what we are injecting is iodinated contrast agents, just to know that in fact we are performing millions and millions all over the world of injections of this product. There is a huge concern of some of the findings, negative findings we may have using this agent. But in fact, it's so safe that we need to inject almost 300,000 patients in order to have one major complication after the use of contrast. So it's very, very safe. The profile is very safe. So because we have the possibility of being so fast with this volumetric CT, this allows us to do or to follow the contrast within the arteries or the veins. And again, I use in my example the blood within the aorta, with the contrast arriving within the aorta, making a peak, and then rapidly being distributed to the visceral organs. In the liver, which is one of the visceral organs, the contrast goes steadily and passes through the liver. And as you can see, the liver is not mostly enhanced by the aorta, by the hepatic artery, but by the second part of its component, which is the portal vein. So the enhancement of the liver occurs a little bit later. And what we want from the medical purposes is to explore the differences between the arterial and the portal and the parenchymal component of the enhancement of the liver. And this is enormous implications on the diagnosis. Let me show to you, just to be more specific on what I am telling to you. So these are the curves that we have already showed to you. This is the acquisition window I was talking about. Look at this image. This image is excellently applied on the good acquisition window. We see a metastasis here in the left liver lobe, another here. Now look at the image a little bit later, just a few seconds away. We see this metastasis, we see the smaller one, but we don't see the metastasis on the left liver lobe. So for this, you can understand if you are performing an examination, you decrease your sensitivity just if you use the wrong technique. And this is, of course, the good goal of volumetric CT and the rapidity of acquisition. Look at, this is a patient with a tumor here. The tumor is hypervascular with a huge liver lesion, a metastasis, but just a few seconds away, look, we don't see practically nothing within the liver. And this type of examinations may be reported as near normal or normal and creating really sense false of security. So we are able to do this. We are able, even because this is so fast, the acquisition, we can acquire 3 times instead of only 2, and do this A1 and decompose in the A1 and the A2 and the portal venous phase a little bit later. And we obtain images of high quality. Look at this image that displays the parenchyma and the portal vein, and to this one that we are even able to show the contrast within the portal vein, but it did not reach yet the hepatic veins. It only reached the hepatic veins some seconds afterwards. And again, to show you the application, look at this case with hypervascular metastases. 1, 2, 3 metastases, very well displayed, just a few seconds away, 1, and we don't see practically nothing. This may be not reported at the very end. So this is the type of information we need to cope today with our machines. Again, the same thing for a hepatocellular carcinoma in a patient with cirrhosis, just very, very well seen on the late arterial phase, but not a few seconds away. The same for the portal venous phase. Look at this image. Now it's exactly the reverse. Now we are too soon in the liver. The hepatic veins have no contrast. The portal veins have contrast, but the parenchyma is not enhanced with full capacity. And what happens? Just a few seconds away, look at the amount of lesions this patient has. All of these are metastases that are not seen on this phase. So this creates, in fact, the need for dynamic imaging. The aggregation name is dynamic imaging of the liver, exploring these different phases. I hope I have explained this to you. Of course, we can extrapolate this from the liver. You can imagine exactly the same or a very similar thing in the brain with tumors, and to understand how the contrast diffuses within the tumors, or in the case of stroke that I spoke before. Of course, we are being we have more resolution. So spatial resolution and temporal resolution, we are detecting more and more very small lesions, very small, what we call the sub-centimeter lesion. And we call it even too small to be characterized. This is one of the problems of CT that is still unsolved until the moment. And the problem is that this magnitude. Look at cancer patients, which are essentially the problem I'm talking about. They may have focal liver lesions less than 1 cm in almost at 13% of cases. And this means just one thing. If I say in my report that there are metastases, this patient goes to chemotherapy. This patient has no metastases, no chemotherapy. So it's very important to understand if I do not have a false positive, for instance. And of course, this cannot be solved by conventional CT. Here we have an example of an image. Even if you go thinner on the slices, like 1.2 millimeter, we just introduce quantic noise in the image, electronic noise. And if you go to 5 millimeters, again, I'm not able to say, is this a metastasis? Is this just a simple cyst? I don't know. And this is the reason why we should do other techniques. Look at this case. This is really worrisome. There is a very, very tiny lesion here. It was reported. And look, just a few months ago, the growing of the lesion, which is in fact a metastasis. So this leads me to go inside the new application of CT, which is dual energy. Dual energy is a concept that is not new at all. It's known from many, many years from the physical colleagues, from the physics colleagues, and it can be achieved with dual or single source of X-rays. But what we do basically is to irradiate the object with the 2 different kVs, 80 kVs and 140 kVs. And as you know, the photoelectric effect is highly dependent and different between 80 and 140 kV, and each material has its own, I would say, signature. So what we are seeing now is a density-oriented material. So we are possibly measuring the chemical composition of material. And one thing that this machine can do very well, this dual energy, is to separate what is calcium from iodinate contrast, which in the conventional CT, they are both hyperdense and I cannot see them. This is the reason why, for instance, dual energy can be of extreme helpful on the trauma patient, because it can separate to you what is hemorrhage with iodinated contrast from what is small fractures, which is calcium. Can you imagine that? CT perfusion is another application that we can, in fact, gain from the use of this technique. So the technique is, as you see, the iodinated contrast material density is modified and decreases when we go from 80 to 140 kV, and we can create, which is different from water, as we see here, simple water, and we can create material density images. There are several possibilities to do it, so at least 3 techniques that are used in the clinical practice. The so-called dual source from Siemens that uses 2 sources. This means that we are leading, this is the reason why we have 2 big sources, or just one X-ray producer, as we see here, generator, but it switches between the 2 kilovolts, which is the case of GE on their approach, or finally the sandwich detector, we radiate at exactly the same voltage, and we radiate at the same time, and it is the detectors that are going to separate what is the spectrum of the X-ray that has 80 kV from those that have 140 kV. So basically, we have a pair of images. This is the pair of images. Of course, whenever you are using lower kV settings, you have more, the effect of the contrast is more conspicuous. And here you can see the pair of images and the blended images from the 2 energies we use in order to characterize. Further now, we did not characterize anything, but we can now choose a monochromatic X-ray beam and be able to analyze the images at a certain energy, like 70 keV, for instance, and we can specify this photon energy and create, in fact, images that are absolutely outstanding and comparable with something we are used to on MR with T1 and T2 weighting of images. We can suppress water, we can suppress iodine, we can use and make virtual non-enhanced images and characterize beta lesions. Basically, the 3 materials that are well recognized is water, iodine, and calcium. Let me show you an example. This is the starting image, so the blended image between the 280 and 140 kV, the 2 energies. Then we say to the machine, to the algorithm, we say, go please and show me only water density, and here we have water density. So despite having contrast within their kidneys or the aorta or whatever, we don't see it. Or on the very contrary, we just say, please reconstruct me only the presence of the iodine, and then it reconstructs, attenuates everything else and show me only the iodine within the organs. This is important because with this, I may obviate the need for having a non-contrast. That's the reason why I can do virtual non-contrast images. Look at this case. This is the blended image. I have here as a lesion. The lesion has something that is very bright inside. So the question now is this calcification from a lesion, or is this iodine uptake of the lesion? So let's go to the material density images. Let's go to the iodine map. And what we see is that the image has this very bright inside. So basically, if I am in the map of iodine, it should not be if it was calcium. And when I look to the water, to the simple water, this is the virtual non-contrast image. the area of hyperdensity disappeared. So this means that, in fact, this is accumulation of contrast within the lesions. If there was calcium, it should display now and be shown here on the water parametric map. So this is the advantage of dual energy CT that is now routinely used on a clinical practice. Look at also in this case, we need to detect very small lesions. We have excellent spatial resolution, but now if I do not go and look to my images, blended images, where I think I have a small lesion here, but if I do the monochromatic 40 keV image, here we have it, and the conspicuity increases, and this is a very small tumor in a cirrhotic liver. Another application that I think it's very interesting, I talked to you about previously about the difficulty in characterizing very small things because there may be partial volume effects. I am not able to understand exactly what I'm seeing. The density is around 30 to 40 Hounsfield units, and I'm not able to say it is some metastasis, it's just a simple cyst. And with using dual energy, what I can do is to calculate the iodine density, the density or iodine map, if you want, inside the lesion, creating a region of interest here. And you can see that there is practically none contrast, less than 1 milligram per milliliter. Again, this is the parametric map just to show you exactly the same. And this shows you that you are dealing not with a lesion that uptakes contrast, but with a lesion that does not uptake contrast. So you can more confidently say that you are dealing with a liver cyst. We can do parametric maps like this. This is important. This is a huge tumor treated with some local regional therapies. The areas that are hyperdense are the areas of viable tumor. But look at the conspicuity we have using dual energy CT. We can even create histograms, total histograms of our parametric map, and then to understand and compute and compare what is happening to these parts of the tumor that still remain viable and should still be treated. So this is one advantage. Now, I'm going very briefly on perfusion. If some of you have been or was watching my lecture yesterday, I've already spoke on this. The principle is exactly the same. What we want is to evaluate the tissue vascularity. I think this is really a clinical need that is not entirely met on the clinical ground. So if we can use it currently and in every case, it would be wonderful. But we don't have, until now, reliable, I would say, evidence to use it, especially in the context of clinical trials. This is the problem. So what we try to see and quantify is the temporal changes of tissue density after injection. And we know this very well. This is made everyday basis on the brain, where we do brain perfusion for stroke assessment to decide exactly if we are going to treat or not the patient with some kind of thrombectomy treatment or something. And I think that the application is very, very important on oncology, because on personalized medicine, we are using more and more not drugs that kill cells, but drugs that reduces the vascularity of the lesions. So this is really the biomarker, the surrogate biomarker that we are interested in. So this is the case of a huge tumor, the parametric map, and the areas inside show the most vascularized areas of the tumor, very simple to see. And of course, I've shown you this example yesterday, I think. This is a tumor with a parametric mass in the liver, very hypervascular. Before treatment, we treat the patient and the vessels go out. Again, look that there is not great change on the size of the lesion. So Do not try to apply any criteria based only on change or morphologic changes, because it's not going to work. You need to work on a different biomarker, and this may be very well one of them. Again, a tumor here that was operated upon, and we see that we are calculating and showing the vascularity within the lesion. We can extract a series of information, and of course, be able also to derive prognostic factors. A patient with a tumor with recurrence after a local regional treatment, here we have the tumor again displaying contrast enhancement to better advantage on the parametric map of this angiographic examination. Beware of the dose for CT perfusion. I've already told you that this was the initial problem with the dose for children that were controlling their tumors, their brain tumors, once a week or once a month with CT, and they have began to appear with side effects of radiation. So beware of that. Use iterative reconstruction, of course, always. If you use dual energy, you are not giving more radiation to the patient. This is wrong to think that we should add up 80 to 140, and we are incredibly using a ultra high dose. This is not true. The dose that we are using is essentially the same, but you can even reduce the dose with iterative reconstruction, and you can reduce the amount of contrast agent you use. This is very important. And of course, we can do like 10.8 millisievert, which is perfectly nice to do for patients for angiography purposes. So with this, it is what I have to tell you for MDCT just now. Now we are living in a world that is changing, and the first change that we need to encompass is AI in radiology and on CT. Well, I tried to elucidate here, and I thank you very much to my friend, Professor Nicholas Papanicolaou, that is in the image. This is his slide, not mine. But you see that there may be an increased workflow efficiency using AI on the triage of patients, scheduling, so whatever and that. So this is very important, of course. But on the support of diagnosis and clinical decision making, this is really outstanding. We can detect more lesions, we can segmentate the lesions, we can elaborate some differential diagnosis, we can do prognostication, evaluate the treatment response. Basically, all they contribute to patient management. And this goes, in fact, from a concept, I'm very sorry, it is this slide I want to show you to you, of deep learning-based CT image reconstruction. So I told you that until now we have modulation of the dose, iterative reconstruction, and now it appears the last kid in the block. And the new kid in the block is, in fact, deep learning algorithms for image reconstruction. And with these algorithms, it's absolutely unbelievable because they can, without losing any anatomical and diagnostic information, they can in fact display the same images. You have a standard iterative reconstruction or with deep learning, and in fact what you are doing multi-phase imaging with 80 kV as a standard dose, which is incredibly low. Normally we have to do it with 80 to, we have to do it with 120 to 140 kVs. So this is especially on low dose objects. And you can see that the gain in amount of dose, it's really unbelievable. Here you can see that CTDI for performing such an examination is only 2.4. This is unbelievable. This is really a very ultra low dose without jeopardizing image reconstruction. So please be aware, this is, I would say, there is not a single vendor that now does not use deep learning image reconstruction. This is why I say that perhaps artificial intelligence is appearing to us as an end product developed by universities to very special purposes. This is one of the purposes. And finally, to end up in my talk, the photon counting CT. And the photon counting is the second kid in the block, recent kid in the block. And the difference from what we have now with the scintillator solid state detectors is that, in fact, we have a two-step to produce an image. First, the photons reach the detector. Then they are transformed in visible light. So there is an analogic to, and then they are transformed in an electric impulse. So there is, of course, a loss of information on this transformation of the energies from light to electricity. But using, in fact, the photon counting, the photons are the photons that, in fact, are responsible for stimulating the detectors, and everything that is radiation reaches, in fact, the detectors, and this creates a completely different setting in our patients, because the individual signal of each photon detected contributes to the final image. And this is really, I would say, a great advantage from the clinical perspective. What we can do many things, but these are, I would say, the four big ones. Smaller detector pixels. So this means that maybe we are going from ultra spatial resolution, giving rise to matrices that abandon 512 to 800 per 800, for instance. We can denoise the image, elimination of electronic noise. We increase the spectral sensitivity of the photons within the detectors. And finally, we are increasing the contrast resolution. Let me show you just one example. This is already a commercial product. I think there are more than 100 units sold already around the world. Unfortunately, they are still very expensive because the material of the detectors is highly, highly expensive. But look at this image. Everything is the same except the detectors. Now, this is analogic to digital. This is photon counting. Look at the images of these bubbles here in the lung. Look at the walls compared to what we see here. So there is no change, there is no comparison, no possible comparison, because the gain in spatial resolution is enormous. Like someone was asking previously, there is also a huge benefit on dose reduction. Also that, and in fact, there is gain that goes around 30 to 40% of dose reduction. So it's my real belief that in the near future, the problem of those constraints on CT will be completely surpassed, and we are going to use CT more and more as a screening tool, as a biomarker tool, without being very, very, I would say, occupied with our minds occupied with dose reduction and reduction of spatial resolution whatsoever. So in my conclusions, I think we have seen in the last years a huge increment on the spatial and temporal resolution of CT. This is the reason why we call it volumetric CT. This is important, this concept. We need to understand that we have to create dedicated acquisition protocols. They may be more prone to spatial resolution. You don't care about temporal resolution, or exactly the reverse. It depends on the clinical indication. The clinical indication is increasing. Please look at the images I showed you on kinematic rendering, and you understand that many things can be shown and solved by this. We are doing a huge reduction on the radiological, on the exposition that goes to our patients. TC of double energy is very important, such as perfusion CT, and of course, photon counting. I think it will be the future. For now, it's really expensive. But this is something that is going to end, and we are going to have excellent image quality at an affordable price in the forthcoming future. I'm sure of that. Thank you very much for your attention. I will finish, and I will finish also sharing my screen at this moment. Thank you.
Thank you so much, Professor Caseiro Alves. It was an excellent talk that gave us an excellent overview of these technical updates that are impressive. And in fact, I had one question, but this was already addressed by you in these final slides. But if you can comment on this, besides all of these incredible technical updates, in the perspective of a radiologist, which are the challenges that must be the priority to be addressed in the next years to maybe to help improve the life of the radiologist?
Well, I think that the major goal that we have is using photon counting. Take it to an affordable technique to everybody. The gains are so high that we are not even scratching the surface of what is the advantage of photon counting. And it's not, as I showed you, the dose reduction is many applications will benefit from that. And I'm sure that the ultra-resolution imaging with different matrices in the capability to see things that we are not able to tackle today will be shown up. I will give you an example. Imagine a patient with bone pain with normal CT examination. If you do ultra high resolution imaging, maybe you see some fractures of the trabecular bone you are not seeing before. So you may diagnose, I would say, faster. Then you can go to different biomarkers like perfusion. I think perfusion will be one of the leaders. And of course, you increase the resolution for examinations that are needed, like coronary CT or even myocardial CT that is also being made for evaluation of the myocardium. So this is an enormous, I would say, bunch of things that will be open with use of a CT. Of course, finally, I think that also for the use of as the support for clinical trials will be more liberalized, and the possibility of having a CT to control the diseases more upfront to show and to study on patients. So I think these will be the future trends of CT. Lower dose, higher resolution, temporal and spatial resolution, ultra high dose, ultra low dose, and ultra high resolution.
Okay. For now, we do not have more questions. I don't know if anyone else, of course.
Can I make a question? Thank you again for your excellent presentation. Every time I hear you, I hear you with very pleasure. I have a question. I don't think, well, I think it's kind of an unfair question because I'm trying to compare the evolution between diagnostic devices and therapeutic in the therapeutic area. Are you afraid that the evolution in diagnostic systems like imaging systems is so fast that you can detect some abnormalities that are not able to be tackled by the drugs and the surgical approaches?
Yes, I think you are absolutely right. I think that there is an enormous change, an everyday change, and I cannot foresee the entire picture of the future, but we are talking today, for instance, on nanorobots. Can you imagine some kind of drug that is specifically delivered to a target? just to the tumor target, and then you can do whatever, even local treatments using brachytherapy or whatever, or that you can see it even 100 times better than using FDG PET. So this is what I'm talking about. I think these kind of opportunities will be for sure open. I'm not saying that imaging will be alone in this endeavor. On the contrary, I think that all the techniques are increasing. It's unbelievable. I think that will show up, will pop up, not for now, but biomarkers of tumor progression that you can use to take your clinical decisions, even in the absence of images. For instance, imagine a patient with a colon cancer, and you have until now a biomarker that is called CEA, which is the tumor marker. But it's not very sensitive. So there are tumors that produce, tumors that do not produce. The changes are, imagine, from 4.1 to 4.2. What's the meaning of that? It's very difficult. But imagine now that you can, in fact, not going to this kind of measurement, but you measure the exosomes that the tumor produces in the peripheral blood, or to derive and see the DNA fragments that are still in the blood, and you can detect them. Although by I don't know, by any technique you can call it, by micro RNA procedures, or even micro MR. I don't know, but I think this is the object. The object is to go earlier and earlier and earlier, and finally to go to preventive medicine. I think that this is basically the goal. Now we are trying to go to try to treat early treatment of patients, but we should go and think about also preventive medicine, and even correction of genetic dysfunctions or malformations will be possible in the future. So it's an enormous avenue of possibilities, but this is how I foresee it. I'm not afraid of competing with nothing, because imaging has enormous capabilities of reinvent itself. Look at the quantity also of techniques that were practically killed at born. I give you one. For instance, think of thermography, very used. They think that breast cancer will produce more heat than the normal breast tissue, and they try to develop, and they sold a lot of imaging for that, and finally the technique was completely discontinued because it was not sufficiently accurate or sensitive and specific for detection of cancer. So you see, things are coming and going, and I think imaging will reinvent itself. I don't know if I answer your question, but it's rather difficult.
Of course.
But I think this is the way. This is the way. Genomics, radiogenomics, and all of that, and proteomics and metabolomics will be connected to image, and will also have an answer. So, for instance, a patient that has a possibility of pancreatic cancer, we are no longer imaging the pancreas because the patient is afraid of having a cancer, and then we scan the patient has nothing, and then 2 years after he has a pancreatic cancer. It happened already. So we need earlier things. These earlier things may be very well from liquid biopsies or whatever. I don't know.
Thank you so much.
Thank you. It's always a pleasure to hear you, Professor. Thank you for your time and presentation today.
Thank you.
So now we will move on to have a break, and we will return to our program at 4:30. See you in a few minutes. So, can you listen to me? No. Yes.
I
Yes.
can hear you.
Okay. So let's start this second part of today's session. And has learned from our previous sessions of yesterday and today, we know that biomedical imaging techniques like MRI or CT scans are crucial for the diagnosis or also the treatment. However, there's a trade-off between image resolution and other factors like acquisition time, cost, and patient safety. Was very clearly addressed also today. So super resolution comes in to address this challenge, and Professor Francisco Caramelo, who needs no introduction at this point of our course, will also comes in to address this topic today. So Professor Francisco, the floor is yours.
Thank you, Salome. I'm going to share my screen. Okay, as Salome told you before, I'm going to speak about super resolution. I'm going to change a little bit the subject because in the previous sessions, the subject was CT, and I'm going to present most of the results in molecular imaging, but the same principles can be applied to any other modality of imaging. So in summary, I'm going to recap some of the molecular imaging principles and talk about the gamma camera that was already addressed by Professor Salome. And then I'm going to move on to the super resolution and define spatial resolution that I also addressed before when I talk about ultrasound imaging, and then talk about the algorithms and present some of the results that we have obtained in this subject. So when we say molecular imaging, we are thinking about PET and SPECT. They are similar, but they also have some differences. So PET, as you know, stands for positron emission tomography, and SPECT for single photon emission computed tomography, and both use radio level molecules, but in PET, the radio tracer is a emitting positron, so there is emission of positrons, whereas in SPECT the emission is of single photons, so there is a difference. In PET, a positron is emitted and then suffers an annihilation, and in the annihilation, two gamma photons are emitted in opposite directions, more or less, very almost at 180 degrees. And in PET, then the two photons are detected in opposite detectors, and this is a difference for the gamma camera, because in the gamma camera we only have one photon, a single photon, so that's the SPECT single photon, and we don't have this kind of collimation. So when we have two photons, we know what is the direction of the emission. So we have an electronic collimation. We can know the direction, but in SPECT, the photon can be emitted in all directions. So we don't know the direction, and to get rid of some directions or to exclude almost all direction, we use a collimator. And the collimator is a big difference between SPECT and PET, and I'm going to address this because it's very important for spatial resolution in the gamma camera. And the other difference is that in PET we have a ring-shaped detector. We can have different architectures also. Professor Nuno also addressed that, but the common architecture is a ring-shaped detector. But in the gamma camera, we have one head or two heads or three heads that can rotate around the patient. So it's different, and also because we have in PET we have this kind of collimation that can give us the direction. We can reconstruct the image using only 180 degrees, but in SPECT we have to rotate the head of the camera in 360 degrees, so it is also different. But the idea, the basis for the image reconstruction is the same. We have projections both in PET and in SPECT, and using the projections we can and then reconstruct the image. So this is an image that tries to portray the difference between SPECT and PET. So the main difference, at least in this talk that I'm going to highlight, is the existence of a collimator in SPECT, and also there is also a difference that using a gamma camera we can have 2D image. We call this scintigraphy, and they are simply planar images, but in PET intrinsically we have 3D images, tomographic images. So the difference between PET and SPECT, apart from the kind of emitter that they both use, in PET a single photon emitter, and in PET a positron emitter. The difference is the collimator. In SPECT a physical collimator, and in PET electronic collimator that comes from the fact that we have two photons instead of only a single photon. Okay, so some fundamental ideas in PET and SPECT is that in both technologies we have to administrate a radiolabel molecule to the patient. So this administration most of the times is intravenous administration. So the molecule is distributed in the bloodstream, and then it goes to the target tissues, and both in the process in the bloodstream and in the target tissues, it emits gamma photons, which can come from the emitter itself in the case of the SPECT, or from the positron annihilation in PET. Then these photons that are emitted from within the body of the patient, they interact with a gamma detector, and we have both in PET and in SPECT we have a gamma detector. They are similar, but they are not the same because the energies of the photons are different. And so in the SPECT, in the gamma camera, we deal with lower energies when we compare to the PET energies. So in PET we have 512 keVs, while in the gamma camera we deal typically with 140 keVs. That is the energy of technetium, but we can also have different energies in SPECT, but in PET is fixed, is only 512. So because of this fact, because of the different energies, the gamma detector in PET and SPECT are different, and also because in PET we needed a fast detector, a very fast detector, while in SPECT we can use a more slow detector for the purpose of detecting the gamma photons. So these detectors then transduce the light, the gamma photons into light using a crystal. The typical way is using a crystal, and then from the light, this is transduced to electric signals that can be used then to determine the radio tracer position and its concentration. And we use different algorithms for image reconstruction using the detected events. So these are the basic ideas for both PET and SPECT. These are some examples of SPECT images. In the left-hand side, we have a brain, and in the right-hand side, we have cardiac images. And the main idea is to see the concentration of the radio tracer, and then we try to interpret the concentration of the radio tracer, knowing what is the target. And for example, in the right-hand side, the target is perfusion, blood perfusion. So we are seeing blood perfusion. These reddish zones, we call it hot zones, and these are the zones, that the areas where the perfusion is higher, and the bluish zones are the areas where the perfusion is lower. And we can see that in some cases where there is a lack of perfusion in cardiac exams, we can associate that to a disease. Okay, so this is the main idea. We have some radio tracers that are associated to some targets, and the images give us the position and the concentration of the radio tracers within the body. Okay, so let me talk a little bit about the gamma camera. The design was developed by Hal Anger in 1958, so it's very old, but it is so good that it actually currently is used without much of alterations. So the main parts are crystal of sodium iodide activated by thallium, and the crystal is also coated with a light diffusion layer, and the crystal serves to transform the gamma photons into light, into UV light or bluish light. And then this light is passed to the photomultipliers, and because of that, there is to be a light diffusion layer. This is it reminds the gel that is used in the ultrasonic imaging, that we have to use this kind of layer to couple the different impedance in the ultrasound, and here we couple the difference refraction index of the light. And then we have a set of 60 to 90 photomultipliers, and with these 6 to 90 photomultipliers we can compute the position where the photon interacts within the crystal. And before or in the opposite side of the photomultipliers, we have the LED collimators. So you can see here that we have the LED collimators and we have the crystal, and then the optical interface, the light diffusion layer, and then the photomultiplier tubes. And from the photomultiplier tubes that transform the light into electric signal, we have an electronic systems that detects the event and also compute the position of the interaction. So the collimator is very important for our discussion. So this is a simple device, is a passive device that is placed between the crystal and the object. And this is a device that can be made of different materials, but the material that is most common used is lead. But it can also be made of tungsten and also of gold, but gold is very expensive, so it's not used. It's not common to be made of gold, but the material has to be absorbing material to stop the photons that come from direction that doesn't interest to the image. And this material is made of thousands of small holes, and in the holes are these holes are distributed in the networks, and through the holes the the gamma photons pass through the holes to reach the crystal. And these holes, the direction and placement of these holes allows to choosing specific direction of the incident photons. And of course, it filters out inconvenient photons directions. For example, if you imagine here this object, so in this object, there is the radio tracer, and the radio tracer is emitting in all directions. Okay, and when it emits towards the gamma camera, it can emit in a tilt direction, but when it reaches the collimator, it is absorbed, so it doesn't reach the crystal, and it doesn't it is not detected. And this is important because otherwise we could not have a clear image. We would have a very blurred image, and we cannot distinguish what is the object. The collimators can be made in different architectures, and the architectures can differ in the type or in the geometry of the hole. It can be a square, can be a triangle, it could be an hexagon, and could be also a circle. And so they are different collimators, and also they vary on the direction of the holes. For example, in this case, we have the holes are parallel between them, so we call this parallel collimator. But we can have holes that are divergent or convergent, and they are used in very specific conditions when we want to amplify or when we want to decrease the image. So for the parallel collimator, the augmentation is just one. We don't have any augmentation, and is the simplest and the most used in all studies. But the spatial resolution that I'm going to define later. The spatial resolution is highly dependent on the collimator. So the spatial resolution, it depends on the thickness of the collimator. You can think about the height of the collimator, the thickness of the collimator. The more, the thicker the collimator, the worse, the better the resolution. Depends also on the size hole, okay, and also it depends also, very important, on the distance between the collimator and the source. So we say that the resolution distance depends on A, which is the size hole, and depends on D, which is the thickness, depends on B, which is the distance between the collimator and the crystal scintillation, but B, most of the times B is constant, so we don't address B. Instead, D, changing the collimator, we change D, and also very importantly is that it depends on Z, and Z here means the distance between the source and the collimators. And the resolution distance is directly dependent on Z. So if Z increases, then the distance resolution increases, and the distance resolution, when the distance resolution increases, it means that it worsens. Okay, so what are the factors that are affecting the performance? I'm here showing just a summary. If the hole size increase, so these are the parameters, and we are considered when they are increased. So if the hole size increase, then the resolution worsens. But the sensitivity increase, and the sensitivity, we can think about the sensitivity as the number of gamma photons that are reaching to the crystal, okay? And it becomes more clear if the hole size increase, then the number of photons that can pass through the collimator increases, so the sensitivity increases. If the number of holes increases, there is no change in the resolution, but the sensitivity increases. If the hole length, the thickness, sorry, if the hole length, yes, if the hole length increases, I call it the thickness, okay? So this is the D factor. If it increases, then the resolution improves. And the idea is that you can see here, if the hole length, the thickness increases, then the field of view, it becomes smaller, than in this case, that the thickness is lower. Okay, so in this case, the field of view is higher, is the same hole size, but the thickness is greater in this case, so the field of view is smaller, and also the distance resolution, so the resolution improves. And but the sensitivity decrease, and why the sensitivity decreases? Because if you imagine that we have different sources that come from different planes at different distance, okay? So if we have a plane, for instance, here, the photons that can reach the detector are only these sources, that are in this line. I'm hoping that you can see the cursor of my mouse, but in this case, the line is much bigger. So the number of photons that are reaching in the crystal is much higher. So the sensitivity is higher, and so if the thickness increase, the sensitivity decrease. And also, if the septal thickness, the septal is this the part of the collimator that is not whole, okay? So we are saying that if this increases, if the thickness increases, if the thickness increases, but the other factors are maintained constant, then the resolution doesn't change, but the sensitivity decreases. Okay, because if I'm increasing the septal thickness, most of the times we are decreasing the number of holes. Okay, and if I'm decreasing the number of holes, then the sensitivity decrease. And the distance from of the objects from the collimator, if it's increased, then the resolution worsens, and the sensitivity, there is no change for the sensitivity. So we have a dependency on the resolution of the distance. If the distance increases, then the resolution decreases, okay, worsens. So there is this kind of dependence that is very important. In scintigraphy and SPECT, we could use different collimators, and we call these collimators as low energy and high resolution, low energy, general purpose, low energy, and high sensitivity. And when we say that is low energy or medium energy and high energy, this is most of the times this is linked to the thickness of the collimator. If the thickness of the collimator is higher, then we can attenuate more energetic photons. If the thickness of the collimator is smaller, then the more energetic photons can pass through. So we can only attenuate low energy photons. So saying low energy is a way of referring to the thickness of the collimator. And low energy and high resolution. So high resolution is linked to the small size. Okay, not only, you know that the resolution also depends on the thickness, but if I'm saying that is low energy and high resolution, most of the times I'm saying that it's not very thick, and but I have very small holes. So the resolution is about 4.4 millimeters, and the resolution here is measured in a distance, is 4.4 millimeters, and the sensitivity is about 83 counts per second per megabecquerel. And the maximum energy that we can use to have a not very blurry image is 200 keVs. So this is good for technician. So, but the sensitivity is not very high, and as Professor Salome told you at the beginning of this talk, there is a compromise between resolution and sensitivity. When we increase the resolution, then we decrease sensitivity, and in order to maintain the number of counts, we have to increase the time of acquisition. So there is this kind of compromise between sensitivity and time of acquisition, and then there is a compromise between sensitivity and spatial resolution. Okay, and for low energy general purpose, this is the most common used collimator. The resolution is about 6 millimeters. And you can see that for low energy, high sensitivity, the resolution is worse, is 8.8, and for high energy general purpose is even worse, is 10.6. We can see that the collimator, we use lead for the collimator, one of the materials that is most commonly used, because for the energies that we use in SPECT or in scintigraphy, the photoelectric is the most probable, most likely effect, and this is the effect that we want to have in order to attenuate the photons, because we want that the photons that have a direction different from the perpendicular direction to the collimator be attenuated. So we use lead because of this particular behavior for the attenuation. And how can we define resolution? So the objective way of defining resolution is defining resolution as the width at the half maximum of a Gaussian that represents the response of the device. So you can see here that I have a orange response and more purples and purplish other response. And if these are corresponding to two different sources, and they are, the distance between them is less than the width at the half maximum, is then when they are summed, they are added together in the device, in the detector device, so I cannot distinguish between them. But when they are far away, and when the distance between them are greater than the full width at the half maximum, then I can distinguish them at two different sources. And when they are just equal to the full width at the half maximum, I can see, or I can start to see, or I can guess that they are two different sources. You can see here in images. So here we have the two objects. We have two tiny sources, but when these two sources, they are apart from each other 10 millimeters. And if I try to detect or to acquire an images of these two objects with a detector that have a full width at half maximum of 2 millimeters, because 2 millimeters is smaller than 10 millimeters, the distance, I can distinguish them very well. And one thing that you can see is that the size of the sources become larger, and if this was a real image, one of the things that we would see also is some kind of sensitivity decrease. So instead of this sources became at in this image, it is apparent that these sources became brighter, but this is not true for a real object. In a real object, they become dimmer instead of brighter. But here I'm just showing the effect for the spatial resolution. The brighter and the dimmer of the sources is due to another effect. But again, for spatial resolution, if the full width at the Elf maximum is 10, which is just equal to the distance between the sources, I can see that it is apparent two sources, and I can say that it appears that there are two sources, but they seems that they are so close that we can say that, well, it's difficult to see that there are two sources. But when the full width at Elf maximum become 15 millimeters, which is greater than 10 millimeters, we cannot distinguish the two sources. And so we say that we cannot resolve. So the distance resolution is higher. So here the full width of maximum is the resolution distance, and you can see that when the resolution distance becomes higher, then the resolution worsens. Okay, how about different modalities? So different modalities have different spatial resolutions and also different temporal resolution. This is a, well, somehow old chart of spatial resolution and temporal resolution. You have already seen in previous talks that both MRI and CT and PET became better, both in temporal resolution and also in spatial resolution. But the relative positions between the different modalities are maintained more or less. So CT is very good in spatial resolution. So this is the spatial resolution, the distance, and the temporal resolution is also very good. But CT is anatomical images, but MRI can be used as anatomical, and here is anatomical is very good. We have good spatial resolution, but temporal resolution is not that good. But for functional MRI, we have a better temporal resolution, but then the spatial resolution becomes worse. And for PET, the spatial resolution is about 4 millimeters, and this, as I said before, is somehow old, because PET currently we can have about 2-3 millimeters of spatial resolution, even in clinical PET. And for SPECT, the typical spatial resolution is about 8 to 10 millimeters, but of course, as you saw before, we can have SPECT with better resolutions, about 6 or 4 millimeters. And there is a fundamental difference between PET and SPECT, and in terms of spatial resolution, is that in SPECT we don't have any theoretical limit for spatial resolution. But for PET, we have a theoretical limit, which is the the motion of the positron. When the positron is emitted, it travels in average 0.2, 0.4 millimeters. So that is the limit, the theoretical limit of PET. But for SPECT, we don't have any theoretical limit or bound for spatial resolution. But also for PET and SPECT, the temporal resolution is not very good. So they are slow image modalities. How can we improve spatial resolution? And of course, we can improve spatial resolution. And let me just go some sideways, because we say that the spatial resolution is defined by the minimum distance to distinguish two different sources. That is for spatial resolution, but we can also apply the same principle for temporal resolution, but then the difference is between two different time instance, or for energy resolution, and then the difference is between two different energies. So we can use the same kind of definition for spatial, temporal, and energy resolution. Okay, can we improve resolution? Can we improve spatial resolution? Yes, yes, we can improve spatial resolution, and the idea is to use a form of enhancing resolution, which we call it super resolution. And the main idea is just we have a limit for spatial resolution. For example, in spectrum, the gamma camera, which is imposed by the collimator. If we can transfer this limit to another device that could have a different resolution, then we can improve the resolution. So the idea is to transfer the resolution to another device that has a better resolution. So in the super resolution, the main idea is to use motion. So we are transferring the resolution of the gamma camera, for example, or from the detector to a motion device that can move with greater precision. So we can know the motion with a greater precision. So the resolution of the motion is greater. So we are transferring the resolution of the device, of the detecting device, to a moving device. And if the moving device has a greater resolution, then we can improve the images. So instead of using just one acquisition, we are going to do several acquisitions, but at different positions. And we know with a better accuracy the positions that we are using to do the acquisition. And because we know the positions with greater accuracy, we can use the different acquisitions to produce a super resolution image. So the idea is something like this. Imagine that our object is a square object with values of 0, 1, 2, 3, 4, 6, 7, 6, 7, and so on. Okay, but our imaging device, when we use the imaging device, the pixel of the imaging device is such that integrates 4 pixels at once. Okay, so we can place this imaging device at different positions, but in each position, each pixel of the imaging device will integrate the pixels of the objects. Okay, so imagine in this position, this pixel of the imaging device will sum 0 with 1, with 5 and 4, given 10, and then we'll integrate 2 and 3 and 7 and 6, which gives 18, and so on. Then if we move the device, or if we move the object, is the same thing, moving the device or the object. The only thing is that we have to know precisely, or at least with great accuracy, the position of the object or device. Imagine that we move the device to the right. Then when we do the integration for the first pixel, I'm going to call the first pixel the upper left pixel. We get 1 plus 2 plus 6 plus 5, which is 14, and 3 plus 7, which is 10, and so on. So if we use different positions, and here I'm representing 4 positions, we can say that we can translate this into a mathematical form. We can say that this acquisitions is my y. So these are the acquisitions that I know, and I want to recover the x. So y is my low resolution images, x is my high resolution image, and a, we call it the system matrix, and the system matrix is the one that relates the pixels from the high resolution image with the pixels of the low resolution images. Imagine that I'm going to call this pixel with 0 the pixel 1, and this pixel with 1 the pixel 2, and so on. The pixel with 2 is the 3, and the pixel with the 3 is the 4, and then the 4 is the 5, and so on. So for computing 10, then I'm saying that I'm summing the pixel 1 with the 2, and with the 5th and the 6th, and so on. So my system matrix is something like this. Okay, so here I'm calling S1 as my pixel number 1 of my high resolution image. X2 is my pixel number 2 of my high resolution image, and L1 is the sum of S1, S2, S5, and X6. So we can say that my matrix system, my system matrix, sorry, is something like for L1 is 1, 1, because I'm summing S1 and S2. I'm not using S3 and S4, but then I'm using S5 and S6, and so on. And when I move a little bit to the right, okay, so my new L1 become a little part or a fraction of S1, so I call it this F11. So this is the fraction of L1, of S1 in L1. Then I'm adding S2 completely, so is 1, and then S3 I'm adding just a fraction, so I call it F321. So this system matrix is known because we know what are the movements that were made. So this matrix is known. So we have this mathematical form. We have this equation where we know the system matrix, and we know the wide, the low resolution image, and we are trying to compute the high resolution images. And you can think that, oh, this is very easy. We can just invert the system metrics, okay? And we can compute X by dividing Y from A, okay? But there is some problems. One of the problems is that the system metrics is not square, okay? So we cannot just invert the system metrics, okay? But you can think about, oh, okay, no problem. I just multiply by the transpose, okay? And multiplying by the transpose, I get a square matrix, and then I invert the multiplication of the transpose with the system matrix, and we call that the pseudo inverse, and we can solve this equation very easily. Yes, but it doesn't work also because we have noise, okay? And most of the times we have to do this using a iterative algorithm, okay? And the iterative algorithm that we like most is the MLMM, the maximum likelihood expectation maximization that Professor Nuno has addressed before in a talk before about algorithms. And it goes something like this. We get the one of the values. Imagine that we have L1, okay? And we divided L1, we distributed L1 by the pixels that are contributing to L1. For example, imagine that I have L1 and L1 is 10, okay? So I have L1 is 10, okay? And contributing to L1, I get S1, S2, S5, and S6, and I'm going to distribute 10 by this 4 pixels. So because these 4 pixels have the same weight, then S1 gets 2.5, S2 gets 2.5, S5 2.5, and X is 2.5, and so on, okay? So then I can say that one of the expected values for X1 is 2.5, okay? And imagine now that I move a little bit, and now I get L1 again. And imagine that I just move an half of a pixel. So then L1 is an half of 0, which is 0, and is 1, plus an half of 4, which is 2. So 1 plus 2 is 3, and then 5, which is 8, and then an half of 2, which is 1, 9, and half of 6, which is 3. So 9 plus 3 is 12. I hope I don't mess the computation. So imagine that L1 is now 12. Okay, so I'm going to distribute 12 by S1, S2, S3, S5, S6, and S7, and I'm going to take into account the contributions because, so this is, imagine that I move just an half, so this is gets an half, and this is gets 1, so the S2 gets the double of S1, and so on. Okay, so for S1, previously I would get 2.5 as a first estimative, so my first guess, and then I have another guess, which is not going to be 2.5, is going to be a different value, and for different positions I get different values, different guess values for x1. So after doing this for all the positions, then what I have to do is just average the expected values for each of the high resolution pixels. Okay, so I get my first iteration guess. And then for my second iteration guess, okay, so this is the value of the pixel of I of the low resolution image at position J is distributed by all the pixels. So as I explained, and then I, for each position J, an estimated corresponding pixels. So I do the same for each position, and then I just average all the positions. And then I do the same, but now in the first position, in the first iteration, all the high resolution images are considered to be 1, but then in the second iterations, they are not now 1, they have a first guess. So I'm going to distribute the values of the low sample resolutions, taking into account the values of the first guess. Okay, and so if I do this a lot, then the final solution will converge to the true solutions. Of course, when we have noise, we just stop early to obtain a good estimative of the true images. So I'm going to show you some of these kind of images, but this is one of image. I'm going to explain this better, but in the left-hand side, we have one of the low sample, okay? And imagine that this is a detector, a device detector with a full width of maximum very high, okay? But then I use this detector and move this detector along the object, and I know very well, with very precisely, the position of the detector, and using several images like this one, several low resolution images, I can use that the algorithm that I explained before and get high resolution images. And just briefly, from the left hand side to the right hand side, we are using, or in the right hand side, to obtain these images, we are using 16 of these low resolution images to obtain this one. Okay, so you can hear a summary of this kind of simulation results. So in this case, here M is just the number of images acquired, the number of low resolution images, and here we have the number of I'm trying to remember. Sorry. Here I have the N is the number of positions, and here I have the number, the image size, the low resolution images. Okay, so the results is such like this. Imagine that we have here with okay, I'm having difficult to remember here, but you can see that this is the resolution gain. Okay, so yes, imagine that in this case, for the bottom row, this is the low resolution. And when we combine the low resolution, when we combine 32 low resolutions like this, we obtain this value, okay, these images, which is very, very, very close to the true images. So this is the idea. If I get a low resolution like this one, if I combine 16 of these images, then I get this one, which is close to this one. Okay, so that's the main idea. Okay, and one of the things that we study is, can we apply this to try to correct motion in SPECT? Because one of the problems in SPECT is that as very very bad, it's very bad in resolution time. So when a subject, when a patient is submitted to a SPECT exam, it must remain still, which is kind of difficult. It tends to move. So the idea is motion is going to blur the image. So if we try to correct the image, can we gain something in correction? So imagine that we have some kind of dynamic acquisition like this. And if we do nothing, we get an image like this one with motion. And the image, if there was no motion, okay, the image that we should obtain is something like this. And you can see that, well, it's not very good. Okay, I'm going to explain a little bit better what these kind of images are we seeing in a moment. Okay, so the idea is that can we try to detect the motion of the object? And what we did is we detected the motion of the object using digital cameras, okay? And then we can just convert the motion of the object into detector motion. As I said before, when I think about super resolution, I can think about the detector device moving or the object moving. Is the same thing, okay? But one of the things that occurs in a gamma camera is that the object moves in the same plane of the gamma camera, but also in the third dimension. So we have motion in 3D. So we have tilting of the line of projections. So we have to convert this our system metrics has to be not only with 2 dimensions, but in 3 dimensions. So we get something like, imagine that our line of projections is kind of a square, a parallelepipedic shape. Then when we move the object, we get a different direction. So in purple, we have a different, let me stop here. We have a different line of projection. So we say that this line of projection is contributing to this one, to the brown one. And we have to compute the intersection between these two parallelepipedic shapes. which is very difficult, but we can address this using a numerical approach, and we can compute the system metrics using knowing what is the motion and then computing the different distributions, the different contributions of the projections lines to the projection line that we think that is when the detector is still. Okay, so the simulations that I was showing, they are simulations based on this kind of phantom. This is a JASZAC phantom. This is just a recipient that is filled with water and radioactivity, and then they have this kind of rods. These are different rods that fill the material, and these rods are not hollow, so they create these cold regions, and so the images this is placed on the head of the gamma camera, so we get these planar images, okay, and so these black regions here are cold regions, and the background is an hot region, okay, and we have different sectors that they are with a different number of rods that are apart from each other at different distance, and you can see that we have sectors with very big rods that they are distance from each other with bigger difference. So the idea is to see how good is the spatial resolution. Okay, so you can see this is a simulation, a computational simulation. This is a real JASZAC phantom, but we use a phantom, a synthetic phantom, which also exists. And here you can see that this is the image without motion. So this is a simulation of acquiring a JASZAC phantom with noise. Okay, so here we are simulating a JASZAC phantom with 0 mega counts. And here we are simulating a JASZAC phantom with 10 mega counts. So you can see here that the image is not perfect because we have noise. But then if we simulate motion, if we simulate motion without any correction, that would be the image that we get. So you can see here that is very blurred. We cannot distinguish any of the rods in the upper row, and in the bottom row you can try, and you can say with very optimistically, you can say that I can distinguish here some rods, but it's very, very, very difficult. But also very important is that when we increase the number of counts, of course, the quality of the image increases. But when we have motion just blur everything. But when we correct the image, using a super resolution algorithm, we get a much high quality image. We can recover the resolution, the spatial resolution, and also if you can here you can see that we recover the resolution and becomes better even when we don't have motion, because we are using the motion to enhance the resolution. So this is a simulation just for translation. So the idea is just moving around the JASAC phantom on the head of the gamma camera. And here the same results, but for rotation. So the JASAC phantom is just rotating around the center of itself. Okay, it's not translated, it's rotating. And we can see the same thing, the same kind of results with motion. The image is very blurred, but with correct images, the spatial resolution is enhanced. And we can also try to tilt it. And to tilt here means that we incline, we tilt the phantom. So this is a motion that is not on the same plane of the head of the gamma camera, is on a different direction, is perpendicular to the plane of the gamma camera. But because we are tracking the motion with digital cameras, we can know what is the different placement of the different position. We call it this a pose. So this is a position and the orientation of the phantom. So we can also recover very well the spatial resolution. You can say, well, this is just simulation, but can we do it in real? Yes, and do it in real. There is a difference because in real we don't know the real image. Instead, here we can know that what is the image without motion. Okay, but here we have only the image without correction. And then we can compare the image after the first iteration of the algorithm, as I explained before, and after the 20th iteration. You can see that increasing the number of iterations, we can also increase, we can enhance the resolution. So here you can see that we are not able to see all the sectors of the JASAC phantom, but we can recover some of the sectors. So the algorithm is very, well, I'm going to say very good, but then again, I'm not the perfect judge. And once again, here we can see that increasing the activity. So when we increase activity, we are increasing the number of counts because we are maintaining the acquisition time. So also the quality of images increases. Okay, the same thing, but for rotation, the idea is the same. So here we only have translation, and here we have rotation. Okay, so in rotation, you can see here that the algorithm doesn't perform very well for low activities, because if we have low activities, then the noise is very high. Okay, so if the noise, the signal to noise ratio is lower, there is no algorithm that can recover anything. So we don't have any signal. So it's not possible to recover if we don't have a signal. And also combining motion. So this combining motion is just tilting and rotation and translation. Okay, and here you can see also that using more iterations, we can enhance even more the resolution. And lastly, I'm going to show you with a phantom that we have built ourselves. So this phantom is very simple. It's just 6 holes, but we have here an area with 3 holes, and each of these holes they have 2 millimeters diameter, and they are further apart of 5 millimeters, these 2 holes, and these 2 ones are 10 millimeters apart. And we have a bigger holes and they have 3 millimeters diameter, and they center from center. They are 6 millimeters apart, and these ones they are 2 millimeters apart. And we fill this with technetium, and then we acquire the images. So, and then we move the phantom, and we move the phantom in a very crude way, because we use a millimetric sheet of paper, and we move the phantom on these papers manually. So the accuracy of movement is not very good, and we did just four positions, so it's not very good. But here you can see that in the left hand side, here you can see that these are the images that are obtained when we combine without any correction the 4 images that we have obtained, and then here these are the images after the image correction. But in this case, we use not only the image correction with a super resolution model, but also we also have a special resolution model, because if you remember, when we are the spatial resolution in the gamma camera depends on the distance to the collimator. Okay, so we use a model that takes into account this distance to the collimator. Okay, and these are 2 different models, 2 different spatial resolutions, that kind of spatial resolution models that take into account the distance, and these are the results. So you can see here on the left hand side that we can distinguish between 10 millimeters, 10 millimeters far we can distinguish, which is what we expected, because we are using a general low energy general purpose collimator. So we think that okay, up to 8 millimeters we are going to be able to distinguish, and of course we can distinguish 10 millimeters. Okay, but we cannot distinguish 6 millimeters. Okay, and of course we cannot distinguish 5 millimeters. But when we apply the super resolution, then we can see that we can distinguish very well 6 millimeters and almost 5 millimeters. But using a different model resolution, we can say that we can distinguish between 5 millimeters. It's very dim, but well, also the trial was very crude, without any care for precision, or care for precision in the motion was not very high. Okay, so but I'm ending my presentation, but the final remark is just to say that this kind of algorithms can be applied, and we can get much more quality images. But then again, this comes with at the expense of using devices to compute the motion, and also most of the time because we need more positions, so we need more time for acquisition. Okay, so there is a cost. We want to enhance resolution, but it comes with a cost, and the cost most of the times is time, for acquisition time, and also a device for measuring the motion. Okay, thanks a lot. I'm going to just break my sharing.
Thank you, Professor Francisco. In fact, there is always a cost-benefit relationship that must be taken into account. Just a very brief question: do you think this super resolution will be incorporated into clinical SPECT scans in the near future, or are we still a little bit far away from that?
I really don't know, because most of the times when researchers are using SPECT, they don't care much about resolution, because they are expecting that the image doesn't have very good resolution. But for animal trials, for animal experience, that is very important. And in that case, I think that well, I don't think that will be incorporated in the scanners, but maybe some kind of devices, external devices that can be accopulated to the scanner. I think so, that can be done, because in animal experiments, we can also have longer acquisitions.
Yeah.
Because the animals are also sedated and they are fixed, but for human, I don't think so.
It's more difficult.
Yes.
Okay. Thank you so much. So I think we can move with our program, and I will give you again the floor, Professor Francisco, to present our next speaker.
Thank you so much. It is my pleasure to introduce Dr. Augusto Oliveira, an assistant researcher at the Centro de Ciências e Tecnologias Nucleares of the Instituto Superior Técnico, IST, in Lisbon. Dr. Augusto Oliveira possesses extensive experience in ionizing radiation dosimetry, radiation protection, and safety assessment. He serves as the head of radiation protection at the Laboratório de Proteção e Segurança Radiológica of IST, and supervise radiation safety assessments for various facilities. Dr. Augusto Oliveira will present a new topic in this year's Biomedical Imaging course, focusing on dosimetry, radio protection of radioactivity sources. And welcome, Dr. Augusto Oliveira. It's a pleasure. When you want to start.
Okay. Thank you very much.
Welcome.
I would like to thank you to Francisco and Filomena to invite me to this talk. So I think I can share the screen.
Yes, please.
Okay. So let's start. Well, okay. Can you see the slides?
Yes, perfectly.
Okay. So, sorry. So let's start. So the summary of this talk, that will be a short introduction, and we will start in the risk associated to radiations, ionizing the radiations, and we will go from the dosimetry to the general concepts of the radiological protection. So, to start, let's say something about the science behind the field of radiation protection. So we need some mathematics, as you expected, but also we have topics in physics and chemistry, biology, geology, ecology. So a lot of fundamental sciences which are concerned with environmental issues and also as also human issues. However, we can add some social sciences like those that you are seeing. And above all of this science, we must have also the law. And so you can see that this field is a multidisciplinary field. And now you may ask, where is the medicine? So the medicine is behind all of this science. However, we don't have time to talk about all of these problems. Well, my talk will be restricted to the topics outlined by the red line. You can see. So where to start? So I choose to start by this number, and this number is concerned with the risk of the associated to ionizing radiation. So you can find that this number in the ICRP 103, and this number is the probability coefficients for the detriment adjusted cancer risks. So how can we understand this figure? So let us make an experiment, which is to expose people to radiation. So let us consider that we have a set of 9,000, more or less 10,000 individuals, which we expose to the 20 millisievert in whole body, in the whole body. Well, it is known that the deaths from cancer deaths are more or less 10 individuals from the set of all of the people exposed. So let's go interpret this data. So what can we conclude? So that the probability of death is 1 in 900, more or less. Which means that we have 0.11% per 20 millisievert, divided by 20, and we obtain the number in the previous slide. So 5.5% per sievert means that the 10 cancer deaths for 10, more or less 9,000 people exposed to 20 millisievert in all of the body. So we can see the sievert has an approach to the probability, or an approach to the quantification of the risk associated to ionizing radiation. So instead of speaking in probabilities, if we are speaking in sievert, implicitly we already are speaking in probabilities. Some cautions that is that this is a statistical result, and we must be careful when applying to a given individual. So it can be only applied to a given individual if the person corresponds to the average individual, and the conditions of exposure are the same, which is the whole body exposure. So in radiation protection, the risk assessment instead of using probabilities, we can use the sievert to express the risk associated to the application. Oh, these come from this concept, the detriment, and the detriment is a technical designation for the harm to the health of a group of peoples exposed to radiation source. So, in the detriment, we must consider the time after the exposure, the severity of the harm, and the probability of the harm. Because we are concerned with the biological effects of radiation, we must consider the absorbed dose, the energy transfer from the radiation to the body, the tissue irradiated, the dose rate, and the age of the individuals. Considering all these topics, the ICRP developed some models where the detriment can be expressed from the total risk of fatal diseases and non-fatal diseases with the corresponding more or less quality of life and the average value of the life lost. So this is a simplistic way to introduce the field of the radiation protection. You can see that we are in the field of the epidemiology because it needs to depend from the study of the biological effects of many people exposed to radiation. So if we introduce the hereditary effects, we can we change from the 5.5 to the 5.7% perceived. So if you are interested in more details, you have the Annex A of the ICRP 103. For the moment, keep in mind that the sievert is the quantity that express the risk from the exposure to radiation. So we need some quantities to control the exposure to radiations, and in radiation protection there are two main types of exposure: the occupational and the public. And for the patient, we will see later on. So the ICRP introduced the effective dose some years ago, and the personal dose equivalent in the committed effective dose. So the effective dose can result from external and internal exposure. So if the source is outside the human body, we are in the external, and when the source is incorporated in the body, we are in the internal exposure. So effective dose is named a protection quantity, while the others are named operational quantities, because they are different quantities but can be compared. So the protection quantities, the effective dose, is used to define the dose limits, while the operational quantities is used to measure the radiation that the people are exposed. And why do we need two different types of quantities? Is because, as we will see later, the effective dose cannot be measured because as we will see, it depends from the organ doses, and we cannot put detectors in our organs because it's impossible. And then something must be used in alternative. So the alternative to the effective dose are the operational quantities. So let us go now to one academic exercise. I have here a list of several applications of the radiation in medicine. And is academic because let us suppose that we don't have shielding and we are in an academic situation where we have our source and no shielding. And let us see for the moment, consider the X-ray machines, which are defined by the kilovoltage and the current. So I put here in this graphic typical values for these parameters. So low values for the bone densitometry of the current, low values of the kilovoltage for the mammography, and so on. The radiotherapy, well, is a much higher parameter in the kilovoltage. So in fact, we are in the megavoltage range. And the first question is, what is the air kerma at 1 meter from the source? So I put here those values. You can read it, and you can see that the bone densitometry and mammography are the lower values. Then we go to the conventional radiography and the CT, and the radiotherapy is much higher than the remainder. So these values, well, you can find these values in the manual of the manufacturers, or we can measure it with a detector. So the academic question is, what is this? What is the distance from the source where we will reach 1 millisievert in 1 hour? And the goal is to have some perception about the difference in the intensity of the radiation sources. So if we are in the primary beam of the mammography or bone densitometry, you can see the distance from the sources. We need to stay to obtain 1 millisievert in 1 hour. So for the radiotherapy, we need to go further apart, more or less 600 meters, if you don't have any shielding in between. Well, these values are you can easily make these calculations, and well, let us solve the problem of the safe distance. So if we consider a source at the center of these two spheres here, and defining the radius of each one, then we can define the particle fluence, and the particle fluence is the number of photons per unit area of the surface. So we want to obtain the relationship between the fluence in the two surfaces. Well, we can make by divided one by another and making the simple algebra, we obtain this relationship between the fluence, particle fluence, and the distances. Well, we know that from the particle fluences, if we apply some coefficients where we have the fluence, you may have those. So, and this is the well-known inverse square law of the intensity of the radiation. And applying this to these academic exercises, so if we have the dose at 1 meter, and we want the dose at another distance to be 1 millisievert, then we only have to make square root of the dose at 1 meter. So for the conventional radiology, I choose these typical parameters, and the square root gives the 200 meters for a conventional radiography X-ray machine if we don't have any shielding in between. So you can here compare with the radiotherapy, where the 200 meters goes to the 600 meters. And what about the nuclear medicine? Well, for the technetium, or for all of the radionuclides, we need some references where we obtain the gamma ray dose constant and simply apply this equation here, where gamma is the dose rate constants. For the technetium, this is the value in these units. So for a typical value of scintigraphies, and after 1 hour, we have only to make this multiplication and give the more or less 30 microsievert per hour. So you can see that the distance is not much lower than the X-ray machines. For the fluorine in the PET, using this activity, well, the distance also is small. Note, however, that if we consider a facility with, for example, 600 patients per week, and each one staying 3 hours in a room, then we have 180 hours per week, and then the square root of the dose at 1 meter gives us the 3.5 meters without shielding. So this academic exercise uses I use the effective dose, but also I speak in the absorbed dose, kerma, and I listed here the quantities and the units. So the units are the name of the sievert and the gray. You can see the photos. And the these are the quantities that have units in sievert, so they are related with the risk, and the air kerma and the absorbed dose. They are not related with the risks. Why is we can see in the next slides. So let us go from the physics to the biology. And so the biological effects of ionizing radiation starts with the physical interactions, which are very fast, as you can see, 10 to the minus 15. The chemical phase of the biologic effects are also very fast. However, the deterministic and the stochastic biological effects can appear only in weeks, months, or even years. So let us go from the interaction of radiation with matter to the sievert, to the risk associated with those interactions. So for that, I consider here X-ray beam with an energy spectrum of 100 kilovolts, 100 kilovolts, and I choose some random numbers of the energy, as you can see in the slide. So, simulating the interaction of these energies with water, this is the photon tracks. Well, the source is at the bottom, and you can see that we have photons with only one interaction, or 2 or 3 or 10. Eventually we can have 20 interactions in this energy range. So you know that the main interactions are the photoelectric effects, the elastic scatter, and the Compton effects. So the notes in these slides are that the end of the photon track is always a photoelectric effect, and there are many Compton interactions in between the photon emitted and the end of the photon track. Also, we can see that the Compton interactions transfer low values of energy to the water, as you can see by the numbers. So the photoelectric effects are the points where the main energy is deposited in the water. So in the radiation beam, we don't have only tens or well, we have a lot of photons emitted from the sources, and here you can see the points of the interactions of 10,000 incident photons with the energy spectrum of this at the upper right side of the image, and at the bottom you can see the energy spectrum from all of the points emitted from the red source at the bottom of the image. Increasing the number of photons, you can see that the density of the points increase, and that the energy spectrum is turning smooth. So where is the absorbed dose? Well, to define the absorbed dose, we have to go to each one of these points. Here is one point of where the photons transfer the energy to the water, and if we define some volumes in the water, let us consider, for example, a box and a ball. And if we sum all of the energy corresponding to each one of the points, and then divide by the mass of the volumes, so we have energy per mass. Well, this is a physical quantity, well defined, with units joules per kilogram, and it was named the gray in honor of the gray I show you in the previous slide. So the question is, you see, I show you the simulation of 10 to the 4 photons, but we can ask how many photons corresponds 1 milligray, which is not very high dose, is well, correspond to the limit for the members of the public. And let us consider, for example, photons with 100 keVs incident in the box with these dimensions. So this is a simple calculation. We have the volume of the box, and we know the density of the water, 1 kilogram per cubic meter. So the mass of the water in the box has this value, and if you want the absorbed dose equal to 1, well, dose is the energy per mass, so the energy is multiply only by 1 the mass. So converting joules in kilo-electron volts, well, and then divided by 100, we need to have 1 milligrays in that box. We need 840 billion photons incident depositing energy inside the box. So 10 to the 4 in these simulations is very far from the real situation. So in summary, to conclude the absorbed dose, energy per mass is defined not in volumes, but with the derivatives, and is the derivative of the expectation value of the energy deposited to matter per unit mass, and is defined at a point. So a final remark is that I speak about air kerma in the previous slides. So the difference between kerma and absorbed dose is the electrons. So if we admit that the electrons are not emitted, or if the energy of the photons, when ionize the water. If we consider that the energy is deposited at the photon interaction point, then we are in the Kerma approximation. If this is not possible, then the manufacturers of the detectors must implement the conditions, a condition which is named conditions of charged particle equilibrium, and then the Kerma approximation can be used. More cautions about the use of the absorbent dose is the dimension of the volume or the mass. So if the volume is large, then we can have attenuations inside the volume, and then the ratio between the energy and the mass is not constant, can be have a variation like this here at the higher values of the mass, and the manufacturers must find the region where the ratio of the energy and the mass are constant, and below these values of the mass, we enter in the range where in the range of the mass values where the ratio of the energy per mass diverge, and we enter in the field of the microdosimetry. Is more or less from the dimensions of the cell. Well, we can treat the cells using the absorbed dose, but below the dimensions of the cells, we are enter in this range of divergence of the ratio from the energy with the mass. So for the exposure to the whole body, and considering the particle fluence high enough in order to have conditions that the absorbed dose can be used, we can define for each organ absorbed dose for each point, and we can, knowing the density of the organ, we can calculate the average dose in the organs. Well, I will not go enter into the details of the mathematics. I only say that for different radiations and organs, the same value of the absorbed dose may correspond to different associated risks. So it is for this reason that the absorbed dose is a physical quantity, but is not a quantity that can be associated with the risk of the radiation. Why? Well, because if we have some absorbed doses here in grays for photons and for example, alpha particles with the same absorbed dose, the equivalent dose is the same value of the absorbed dose for photons, however, is 20 times higher if the radiation is is alpha particles. And the organs have to also to be considered, and we have tissue weighting factors for the different organs listed here. And you can see that we have an evolution in time, and the ICRP 103 from 27 is the value that we use it today, nowadays. And we have, if we know the equivalent dose to each one of the organs, then this sum gives us the effective energy. So here we can see that to define the effective dose, we need to know the dose in each of these organs, and we need to have a detector in each one. So it is impossible, and then the effective dose is a non-measurable quantity. So why those values for the tissue weighting factors and the radiation weighting factors? So is because the concept of the detriment that I introduced in the beginning, and results from the study of the biological effects of the radiation and the epidemiological studies. So the application of the effective dose to a given individual cannot be done. We cannot use the effective dose to express the risk of a given individual. We can only use it to a collective of several individuals. So in the medical field, when we use the effective dose, we are the goal of using effective dose in the medical field is to compare different procedures in the clinical applications. So we have here a summation, but note that this is in fact a weighted average of the equivalent doses of the organs. So these slides is only to show where we can apply the effective dose. So in general, the radiography has these values for the effective dose, and we can compare with, for example, the interventional, where we have one order of magnitude higher of the effective dose, and another order of magnitude increase in the CT. And we have here some values for the nuclear medicine. So this is the well-known those limits for the recommended by the ICRP. And after the publication of the ICRP, the limit for the length of the eyes was decreased to 20 millisievert. In summary, we have protection quantities, the effective dose, and the operational quantities, which are the ambient dose equivalent and the personal dose equivalent. which are measurable quantities, while the effective dose cannot be measured. So using the KERMA, we can enter in the field of the medical physics, where the KERMA is the main quantity used, and I put here the geometry associated with the X-ray machine, and where some reference can be associated by measuring the air KERMA area product and the air KERMA incident and the entrance surface air KERMA. The relationship between these last quantities are the backscattering factor, and these are the quantities that can be used to as a reference for the applications in the radiodiagnostic. In the field of the nuclear medicine, or the internal exposure, or the incorporation of radionuclides in the body, the situation here is a little bit more complex, because we have to define some compartments associated, in this case, with some organs, and between each compartment we have a transfer between compartments of the radionuclides. And for example, between two compartments, 1 and 2, here we have to know that transfer constant between between the compartment 1 to the compartment 2, and this situation corresponds to a differential equations. So the differential equations are this one. So the derivative of the activity in the compartment 1 decreases and is defined by the transfer constant of the activity in the compartment 1 to the compartment 2. You can see that we have one equation for each compartment. So you see this system here, where we have a system of differential equations. We have to solve, and we only can solve using computers. And after that, if we have the activity in each one of the compartments, then you have to calculate the dose of each compartment due to the activity of the other compartments. So you can see that is a complex subject, and the people that are working in internal dosimetry is the only work they do, because is a complex problem. So to conclude my presentation, I will go now to the principles of the safety culture. So this publication, which is a small publication with only 16 pages, when the IAEA published this report, I was member of the Radiation Safety Standard Committee well, they write, they have a error in my name, but I recommended to you I recommended to read this, to start to read by this the reports of the agency. I recommend to start with this publication because it is at the center of a lot of other reports. So at the center we have the fundamental safety principles, then we have safety requirements, and then a lot of safety guides. So in the rest of this talk, I will approach a little bit the principles that the agency recommends. So the principles are 10 principles. We only go to the first 6. So here we have the principle, the known principles, the well-known principles of radiation protection, justification, optimization, and those limits from the ICRP 103. We have principles for emergency situations and environmental situations, the principles 7 and 10. And let us see some questions around the 6th first principle. So the principle 1 is the responsibility for safety. So if you work in, for example, in an hospital, the administration of the hospital is the first responsible for the activities, the facilities and activities with the radiation sources. So the licensee is responsible for establishing and maintaining the necessary competences, provides training, implement the safety culture with procedures and arrangements, verify the design of the facilities, considerations concerning the control of the radioactive material, and considerations about the radioactive waste. So this is the prime responsibility for the organization responsible for the facility and the activities. Next, we have obligations for the government that consist in have a legal and governmental framework. So we need to have legislation, regulations, and other standards and measures. So this is the role of the government. And the principle 3, the third principle, complements the first one and is concerned with the leadership and the management. So well, is concerned with the application of the safety culture, which includes attitudes, behaviors, the organization of the safety culture, and the responsibility of all of the individuals concerned with the the facilities and the activities. And then we go to the well-known ICFP principles, so justification. Here, let us note that there are some differences between the non-medical and the medical applications. So in the medical applications, we have three phases. One is that the application of the radiations in medicine is generally justified. The second step is that a given procedure, for example, mammography, is or not justified, and then on the given specific patient is justified to make, for example, mammography or no. So, and this relies on always in the clinical judgment. So the need for the training in the radiation protections in the medical field. The optimization is the well-known ALARA principle, well as known as reasonably achievable, and it must be considered the graded approach. So the safety culture of the conventional X-ray is obviously different from the safety culture of a nuclear power plant. So it must be make a graded approach to the safety of the different applications. The definition of good practices and some factors to have in mind is those you can read it. So this is the application of the optimization principle. And last, the limitation of the risk. So the limitation of the risk is implemented, defining the dose limits. And for the medical applications, we only have to consider that those limits are not applied to patients. For the patients, we must consider the dose reference levels that can be defined at the hospital level, at the facility level, first at the facility level, then at the hospital level, and eventually at the national level. And for these applications is here where we apply the parameters that I used in the first slides for the distance, but also for the time and also for the shielding of the facilities. So in concluding, remember that basic recommendations, when using radiation sources, know the source of the radiation, what type of radiation, what energy, what are the doses or the radiation fields. Then you must have radiation monitoring using the appropriate detectors with knowing the response of the detectors and make the metrological verifications and know or making the correct interpretation of those measurements. And finally, when you go to work in a facility, ask for the radiation protection program and for the radiation protection officer of the facility and the activities. And that's all. If we have some questions.
Thank you so much for your interesting presentation and very pedagogical one. I don't think that we have questions from the participants. I do have a question because you show the effective dose in different countries, and I wonder why they are so different between UK, United States, and Russia. In some cases, there are a difference of almost 10.
Well, I don't know answer that question because I don't know the applications in the another countries, but well, it's a fact.
But they use different vendors. They use different machines, or
Can be a reason. Well, the list is the United Kingdom, the United States, and the Russian. So
yes, and I notice
if you have the other countries, we can expect that the concerns about radiation protection can be different from country to country. Well, I do not, the list don't have the values for Portugal because eventually we will have we can have very surprised about the values of the countries because we don't know the values for Portugal.
okay. So and they are some.
We know that in some cases, in some, for example, hospitals, some people don't care about
the dose
with the dose, and then
yes,
they can be higher.
and yes, and one of the problems always when we talk with doctors is that the dose is estimated for the population and not for the individual patient, and
Well,
in some case,
the estimation for the patients, for the individual patients, we are in the field of the medical physics. So it's a problem to define the dose of the organs for specific individuals. So well, is not the radiation protection. Well, you can see it at the radiation protection issue, but it's also a medical field issue.
yes, of course, because you have a benefit from having the exam, of course.
Yeah.
Okay, I don't think there is any other question. So we can now finish the session here. Thank you again
Thank you
for your talk.
Mhm.
I
Well, I thank you the invitations and well, thank you to Filomena and to Francisco.
thank you.